Good morning, everybody. Today we're going to talk about some biomechanical research in total knee arthroplasty, because I assume that you know now how knee implant is implanted, and we're going to look at the next two lectures what type of research people have been doing and also what our laboratory has been doing. So in this presentation we're going to look at four aspects. We're going to look at functional analysis of patients after receiving a total knee replacement. A total knee arthroplasty is the same as a total knee replacement. We're going to look at fluoroscopic analysis of two types of prostheses, a PFC and a CKS. Those are two brands of prostheses. Changes in patella location after a total knee replacement. Okay. And issues around high flexion total knee replacement. Okay. So first we're going to start with a functional analysis, and you could do a functional analysis of a patient after the patient receives a total knee replacement in many ways. You can do gait analysis, you can look at how people walk, and we looked at how people stand up from a chair. I will show that. So this is a clinical study, and the question was, can we measure progression of functional recovery in the post-operative time of these patients? We have 38 patients, and we measure these patients pre-operatively before they go for surgery, 6 months and 12 months after surgery, and we have a control group of healthy individuals, because then we can compare whether patients stand up from a chair similarly as healthy people. So we call it the electric chair, which is not a nice name, but it is actually electric. And so it's very adjustable, because we want to make sure that a person would start from a 90 degrees of flexion. So this is adjustable, because if you have a change in height, you need to compensate for that. And also you can see here two force plates, and the force plate will measure the force that is applied by the foot on the ground while standing up. Okay, so if one leg is heavily injured, the person will use more the other leg. So it's also a way to quantify how symmetric the legs are functioning and how well the total knee replacement is doing. So this is how it looks like. So the patient has the arms in the side because she should not swing the arms to help standing up. So we want to have it very protocolized. And we measure how she's standing up also with accelerometers. You can see these devices here on her knee. Can you see that? And on her ankle. And that allows us to quantify the angles and the angle velocity of her knee while standing up. So if she would stand up very slowly, we can pick it up, and if she would stand up very quickly. And we measure the ground reaction forces left and right. Okay. Now this is an example of the outcome. So she's going to stand up, she's then accelerating and then slowing down again. Okay. And this is the knee angular velocity of a control group. And pre-operatively, it's the black line, so very slowly. After 6 months, we see the green line. And after 12 months, you see that it's getting closer to the control situation, but not yet there. But we can quantify here, and these are the maximum values. You can see this is a pre-operative, 6 months, 12 months. You can see that it's progressively improving, but not yet at the same level as healthy people. So we can measure how people are doing, basically, with this rather simple test. That is something maybe biomechanical engineers can work on. When we look at the asymmetry of the force plates, 0 means that the person stands up quite symmetrically. Yeah, so the healthy controls stand up quite symmetrically. And you can see pre-operatively, the patient is trying to put more weight on the healthy side than on the involved side, where the implant, where the pain is. And then after 6 months, you can see that it's reducing. And after 12 months, it's almost the same as the control. So from a force point of view, after 12 months, the patients recover. From a kinematic point of view, that's not the case. So there are still differences, but after 1 year, on an average, people are quite well recovered. Okay, so the conclusion of this small bit is that the rehabilitation during the post-operative time of the TKA patients can be measured with this sit-to-stand movement. Okay. Then we thought, okay, can we measure then the functional effect of 2 different knee prostheses? So we have one group with PFC prosthesis from Johnson & Johnson, and we have another group of CKS implants, and that is marketed by Biomet. So these are just 2 different prostheses, and we have a control group. And we measure these people 1.5 years after surgery. Okay, so these are 2 different prostheses, and there are 2 differences. The CKS prosthesis is completely symmetrical, exactly symmetrical, whereas the PFC is asymmetric. They call it anatomical, because the groove has a certain direction. This also means, for example, that this implant cannot be used left and right. So there is a left side and a right side for this implant, whereas the CKS can be used on the left side or the right side, it doesn't matter. Another difference is that the PFC, both of the prostheses are cruciate retaining. Okay, so the surgeon will not remove the cruciate ligament. And the cruciate ligament is here. You can see that. So, I mean, you can imagine that. The cruciate ligament is acting here. And you can see here there is a slope in the polyethylene. So it's guiding the cruciate ligament. In the CKS, there is no slope. It's a sharp edge. So the PCL has to curve around this sharp edge. In retrospect, we think that this is not good. From a mechanical point of view, you should not have a sharp edge with a ligament running over it. But at that time, when we treated the patients, we didn't realize that. Okay, so pay attention to that. The PCL is maybe having a problem with the CKS. Okay, so after 1.5 years, we measured these patients with the test, but we also asked some questions, and there are different scores. I thought I include that here because patients are typically asked how they do. So we can quantify a lot, but questionnaires are also very important because you can quantify that the patient is doing very well, but if they say, yes, doctor, but I have a lot of pain, yeah, the surgery has failed. So there are questionnaires, and they score the pain, the stiffness, and the function. It's the WOMAC score, that's a very famous score. The International Knee Score is also a scoring form, but then specifically for the knee, and the WOMAC is more in general for the legs, let's say, for the whole lower extremity. Okay? What we also measured is the strength of the muscles with a maximal isometric contraction test. Okay, so we do the sit to stand, and we do force measurements that you can see here. So there is a force transducer here, and we strap the leg, and we ask the patient to extend or to push, and then we can measure the power of the muscles, okay? Because we think that it is also important for functioning. The results of this were that the questionnaires did not make any difference between the 3 groups. So the control groups and the 2 prosthetic groups didn't have any difference. And we see that a lot. So in questionnaires, it is vague. You know, what should you fill in? Do you have pain? One says, yes, I have a little bit of pain. And the other says, well, I don't want to complain. So I fill in no for the doctor. He has done the best he could. So I fill in. So it's very subjective. And object measurements will become more important in the future. I'm sure about that, because we want to quantify everything. You have to fill in, everything is now quantifiable. So when we looked at the IKS form, which is more dedicated to the knee, we saw that for pain, there is no difference. For the function, the CKS group scored lower than the control group. Okay, and in total, the control group scored a little bit better than the two prosthetic groups. Okay, but the CKS didn't do so well. When we looked at the strength, so let's say the hamstring, this is then flexion, and the quadriceps is for extension, we didn't see any difference. So we measured it in the prosthetic leg, but also in the contralateral leg. So this is the healthy leg. So we measured also the healthy leg. You can hardly see any difference. It's a little bit stronger, but not so much. Okay, so strength measurements are apparently not so sensitive. When we looked at the velocity, so how people were standing up, we could measure a difference. So again, this is the angular velocity that I showed before. We can see the PFC patients are close to the control group, but the CKS patients are not close to the control group. So these patients are doing worse than these patients. Okay, so something was wrong with the CKS patients. So in conclusion of this bit was that patients with the CKS prosthesis function not as well as compared to patients with the PFC. About 1.5 years after surgery, that was our time point that we measured. And at that time, we decided in the clinic not to use the CKS prosthesis anymore. Okay, so we moved on and we wanted to know exactly the reason why this was. So we did a fluoroscopic study of the two prosthetic types that I just showed you. And a fluoroscopic study is basically that you study the kinematics of the knee using an X-ray camera. So this is an X-ray camera, and the person can walk on a treadmill. You can see the patient is walking on a treadmill, and we can film the inside of the knee. And this is Scott Banks from Florida, and we work together with him because he's specialized in that. Okay, so how it looks like is this. Okay, so what you can see here is the X-ray movie, but in orange you can see that the CAD files of the implants, so the computer files, the design files, are projected on it. Can you imagine that? So on the X-ray you will see a shadow of the metal, and what we can do in the post-processing, we can align the CAD file such that it matches with the shadow of the metal. And in that way we can determine how the femoral component kinematically behaves relative to the tibial component. Okay? Right? So what we then basically do is we can determine how the femoral component moves relative to the tibia. So we can, let's say, put the tibia in a certain coordinate frame, so we can put it still, and then relative to that we can see the movement of the femoral component. And you can imagine that different designs move differently. And the question then becomes, which one moves most healthy? We can kind of calculate that. Okay, so we did this fluoroscopic analysis, and it's quite elaborate, so the groups are quite small. 11 patients with a PFC and 10 patients with a CKS. So with the CKS there was a bit of a problem with the recovery of the patients. And we do this about 3 years post-operatively. We did this in collaboration with Scott Banks from Florida, the person that I just showed. And we looked at a deep knee bend. You can have all kinds of activities. It becomes a really big study if you're not limiting yourself. So this is a very complex graph, And basically it shows the axis of the femur projected on the tibia. Okay, so the femoral component will rotate and translate, and there is an axis of the femoral component, and if we project that on the plastic, that is what you see here. Okay, during flexion and extension. Okay, so for example, red is the axis projected between extension and 15 degrees of flexion. Now, and you can imagine that during flexion, you have all these axes projected. Now, one thing you should see is that the CKS is more to the front than the PFC. Do you see that? PFC is more on the back. This is the back side, huh? This is the front side. You can see that the PFC is more on the back side. This is logical, perhaps, if you know that the PCL pulls the femoral component to the back. So here the PCL pulls the femoral component to the back. That's why the axes are on the back. The CKS remains more to the front, apparently because there is the tissue of the PCL is damaged and doesn't pull it back. Okay, so this confirmed to us that there's something wrong with the PCL because of that sharp edge. So again, we have a sharp edge here. PCL is maybe ruptured or cut. Therefore, the component stays more to the front, and that's not physiological. In the PFC, they have made this slope here. You can see the nice slope. And of course, the engineers have thought about that, and basically all components have that. If you want to retain the PFC of the PCL, there is a slope. So this is just a kind of, the CKS designers forgot that. And therefore the PCL is functioning better than here. Okay, so you've seen this movie before. So this is now the PCL. And you have to imagine if this is gone or cut, this bone can move to the front without any problem. Yeah? Okay. Okay. So this is the sharp cut, and this is the nicely slope facilitating articulation of the PCL with the plastic. Okay, so you can imagine that with the X-ray machine, the fluoroscopic measurements, the field of view is about this size, and the person has to remain with the knee in the field of view of the camera. So it's very artificial. So what people are designing now are robots that follow your knee. They follow the knee. So if you move, the robot follows you. This is a movie about that. So you have the robot. So there is a sensor on the knee, and the robot knows where he has to look at with the X-ray camera. You can see that he follows. So the person can now walk around freely because the robot will follow the knee instead of the knee has to always, the patient has to be attentive to remain in the field of view. Shall I run it again? This is still experimental, but it's, I've seen now a number of laboratories that generate these robots. And as a biomechanical engineer, I get excited by this, of course. This is quite cool. It also allows all kinds of different activities. You can walk around, you can turn, and that we couldn't do that in the past when we only had one camera and you had to remain in the field of view. Okay, so this was the fluoroscopic analysis. Changes in patella location after total knee arthroplasty. So we did a cadaver study, and you can see the cadaver study here, and this is a cadaveric knee in which we used a zipper, and the zipper was used because we didn't want to open up and suture back the capsule every time, because the patella is embedded by the capsule. So the patella is here, the front. The patella runs here, and it's being held by a capsule. If you do surgery and you cut through the capsule and you suture it back, the patella might move a little bit because of the suturing. If you want to then say, okay, I want to replace, I want to do some variables, so I want to put in another implant, and you open it up and you suture it back, you affect thereby the patella position. So we thought, okay, we suture it, or we use a zipper, we open it up, we do something different, and we zip it back. That has no change. There's no change. We do not suture it as a surgeon would do. That's why we use here the zipper. Now you can imagine if the patella moves on the groove and it is not in the same position as in the healthy situation, but it's shifted, let's say 1 centimeter, you can feel that very quickly. Oh. You can imagine that the structures around the patella are very sensitive. Okay, if you, for example, in hip surgery, it is very forgiving because the tissues are very strong and they are very forgiving. In the knee, especially around the patella, it's very sensitive. There are a lot of nerves, and if the patella is not exactly at the same location, the patient will feel that. It's an unnatural patella tracking. So there will be very quickly pain. So we decided to see the difference between the patella tracking intact and after putting on a prosthesis. Okay. So we made CT scans of this knee and we recorded the kinematics of the tibia, of the femur and the patella. Okay. And we do that before and after putting on an implant. So this is then an animation of that. So we're going to look how the patella tracks before and after putting on this implant. Okay. And what you see then, this is a curve of the patella tracking, and this is at 90 degrees of flexion. So this is at 90 degrees of flexion. Where is the patella? Okay, from the medial and lateral side. This is the natural situation. So it moves first a little bit natural if we go to extension and then to the medial side and then to the lateral side again. It doesn't matter so much. You don't have to remember that. That's too difficult. The point is here that if we put on an implant, zip, we move it 6 millimeters. So before it was running a little bit laterally, we put on this implant and then it moves 6 millimeters to the medial side. So there is an offset. So in this cadaver setting, to me as a mechanical engineer, it means that the implant is not designed according to the anatomical dimensions. So we were wondering whether that also would occur in patients. So we measured that intraoperatively. So intraoperatively, in 61 patients, we measured the groove of the bone of the femur and the groove of the implant. Okay, because the groove is where the patella has to run into. And we had 3 different surgeons and 2 implants. It doesn't matter for now. And basically, what we found is that there is a 2.5 millimeter offset. And for some surgeons, it depends on the surgical technique. And we can maybe ask later on the surgeon today how he does that. It's 4.4 millimeters, but sometimes it was 9 millimeters. Okay, so and it's almost all to the medial side. These are all plus. You see, so that is all moved medially, which means that the designers of these prostheses have an inherent error of medial translation of the patella. Strange, huh? And almost all designs have that. And the reason is that you can see here an implant, and you can see here the groove. And the groove is very symmetrical. So the medial and lateral condyle are exactly as wide on both sides. If you look at a bone here, this is the medial condyle, it's wider than the lateral condyle. So if I place now something which is symmetric, I'm going to run here, right? Because this, if I divide this by 2, I'm going to run here, the groove, and not here, because this is the patella groove in reality. Symmetrically, it would be here. So apparently, what we need, there is, I think, one design that has an asymmetrical condylar design. So you need to have a medial and lateral condyle that is different if you want to optimize patella tracking. And you could say, well, does it matter? 2.5 millimeters or 4 millimeters? But the current problem in total knee arthroplasty is pain, anterior knee pain. So anterior knee pain means pain on the frontal side, on the front side of the knee. And it's very diffuse. Nobody really knows where it comes from. But we think that one of the issues is an not normal patella tracking and the sensitivity of the tissues around that. Okay? So the last bit is about high flexion in total knee replacement. And that's, I think, an interesting topic also for you, because in India, people would like to have high flexion. In Asia and the Middle East, because normally an implant is made up to 120 degrees of flexion. And for the Western world, that is enough. Our patients usually don't flex further. And it's very successful also. After 10 years, there is a survival of 90 or 95%. It doesn't mean that people don't have pain. But so the implant is in the body. About 25 of the patients report pain. But nowadays, of course, the patients become more active, and especially people in Asia and the Middle East, because of cultural and religious regions, they want to have higher flexion. So companies are designing now implants that allow higher flexion, at least higher than 120 degrees. Because you can imagine this is much more than 120 degrees. So you can see all these companies. So Zimmer is a company, Stryker is a company, Dept, Smith & Nephew. They all have their own high flex solution to offer to the patients that require high flexion. Now this is a typical example of how that looks like. So we have a standard total knee replacement, and we have a high flex total knee replacement. Okay. So if you look at this bit is made thicker. So basically, the surgeon has to remove a little bit more bone. Yeah? And that is done because after 120 degrees of flexion, beyond that, the metal is going to dig into the plastic because of this peak. Okay? Whereas if you make that curve longer, there is more load transfer. You know, it's a better, smoother load transfer, so the peak stress is not as high on the plastic, so it protects the plastic. So we analyzed that in a biomechanical model. So this is a very simple finite element model. So you can see here the tibia and the fibula. This is a polyethylene component here. It is a rotating platform. We discussed that the day before yesterday. We see the patella. It's not resurfaced. There is no plastic cap on it. And we see the metal component, which is assumed to be rigid. Okay, so, and we apply a force on the ankle. I show it here, but it's basically here on the ankle, as if you do a squat. And then if you release the quadriceps and you apply the ankle force, it will flex automatically, the model. Yeah, so you give your quadriceps muscles, you release them, and that's why the knee is bending. Okay, so because then it stretches the quadriceps again, and there is an equilibrium, a force equilibrium, and here the prosthetic components can find their own position during that increasing flexion. Okay, so you can imagine that we can calculate the stresses on the plastic. And we don't want to have peak stresses on the plastic because that will result in wear. So we have high stresses at 90 degrees, but they increase at 120 degrees, and at 150 degrees it's even more. What you can also see is at 90 degrees, there is no stress on the post. So there's a post here. So it's the cruciate ligament is removed because we now have a post-cam mechanism. Yeah. So there is no cam loading, and here you can see that the post is doing a function. So at 120 degrees, there is a post-cam interaction, and that's logical because in extension the PCL doesn't do anything, and when we bend, the PCL starts to push back. We have here a post-cam mechanism that replaces the PCL. So in extension, the post-cam mechanism doesn't do anything, but when we flex, it starts to push the femoral component backwards. So there is no stress here on the post, but there is stress here on the post. And if we bend further, it's increasing. Okay? So if you do the calculation, you can see here in a normal component that we get digging of the plastic, and here we can calculate that it's not digging into the plastic. You can see it here once more. This is not good, and this is better. But the surgeons don't like to remove more bone than absolutely necessary. So if they have a patient that does not require a high flex design, they prefer this. If they know that the flexion will not be beyond 120 degrees, because then they have to remove less bone. Okay, so there are a number of issues with high flex. So the mechanical factors involved in deep knee flexion that I'm going to talk about are posterior impingement, thigh calf contact, kinematic issues, the PCL and how important that is, and stresses generated at high flexion. I will go over these topics. So first of all, we have seen an animation of a knee surgery before. And do you remember that the surgeon opens the knee from the front? In many cases, there are osteophytes. You can see them here lighted up. So this is bony bits, the spurs was indicated, or the osteophytes. So the surgeon opens it up from the front and cannot see, it's difficult to see for him on the backside what is there, what is present. So he can see on the x-ray that there are osteophytes, and during surgery he has to go on the backside to remove these osteophytes. You can see here that the osteophytes are still present, and you can imagine that this patient is not able to bend the leg because the osteophytes which are connected to the femur hit the tibial component. So it's just jamming, okay? So what he should do is, if you see these osteophytes here, is to remove them. So here you can see that it's nicely clean and that the leg can be bended. So they call this a clean out technique. So surgeons that use high flexion designs and expect from their patients that they really go in high flexion, pay extra attention to the backside and remove all the bony bits. Okay. Now, Mr. Goldstein has demonstrated that by assuming an osteophyte here, and if you have a big osteophyte, you can only flex to 106 degrees, and if it's smaller, you can bend further. You can imagine that. It depends on where you put it. It's just a demonstration, but for you to remember. Okay, so there are many different parameters that affect high flexion, and this is a complex drawing, but it's simpler than you think. So a variable that decreases maximum flexion is if there is bone sticking out. So here you can see, if you look carefully, there is bone sticking out here, and this bony bit will hit the plastic. That is not good news, because then it means that it will damage the plastic, but also will limit the range of motion. So it should have been removed here. If this distance in total is small, it will hit the curvature of the bone. They call this a small posterior offset. So this distance relative to this is the offset. If that is small, then you also will hit the bone and the plastic. So that limits it. Okay, so if there is a large anterior distance, so if the femur is far at the front on the tibia, so then it will also hit the plastic. So for example, here you see that it's on the back and it can flex much more. If it's more in the back, more flexion. That's why it is so important to have the post-cam mechanism or the PCL. And what the surgeon does is a small, if there is a small posterior slope, this also will hit the bone, because usually they make some slope in the tibia. You can imagine if this slope is increased, the leg can bend further. And if the surgeon decides to not have a slope, well, there is less flexion possible. Okay? This is a picture from Professor Peter Walker. He is the guru. He's now in New York. He is one of the most famous designers of knee replacements. Okay, so as I told you, maybe not all patients require a high flexion implant. For example, this patient, due to the soft tissue, cannot bend further than 118 degrees. And this patient cannot bend further than 115 degrees. So it doesn't make any sense to put in a very expensive high flex implant in these patients. So the limit in most patients in flexion is calf to thigh contact, thigh calf contact I call it. So we're going to look at thigh calf contact a little bit more, because from a biomechanical point of view, that's also interesting. Because if you do a rigid body analysis, like a mechanical engineer would do, if you would simulate a squatting, and if starting from standing, we don't use the quadriceps. If you stand, you don't hardly use your quadriceps. And if you then bend your knee and you go further, you feel your quadriceps firing, right? And if you're then almost squatting and you're resting almost on your calf, almost, you feel that you generate the most effort. So you generate also the most pressure in the knee because your muscles are pulling so hard. And so that is what we have simulated in the past. That this is also what I simulated in that finite element model with the ankle load. We do not simulate thigh calf contact. But of course, people squat all the time, and they do not fire the quadriceps all the time, so they can just sit on their calves without using these muscles. So thigh calf contact reduces forces in the knee, and almost everybody ignores that. So what we did, this is a picture from 2007 of my lab. So this is me. I was looking much better. And so Jorrit Selle, this is my PhD student. He did this work, and we took some students. That's how it goes. Huh? We took some students and we measured their thigh calf contact conditions. So what we did is we have here a pressure sensitive mat from TechScan. Okay, so it measures basically how much force is distributed, in this case, from the thigh to the calf while kneeling. But what I show here is a squatting. Yeah? So for standing, and then at some stage, of course, from the knee pit, you measure a certain force. It starts at the knee pit, of course, because that's where the first contact is, and then it starts to become larger. And we measure how much force there is distributed. Turns out that on an average, the thigh calf contact force is about 70 to 70% of the total body weight in 2 legs. So it's quite huge. It's really huge. And this aspect is ignored by most of us. So here you can see the curve. So you see that with flexion angle, the thigh calf contact increases. Yeah, and it starts around 120 degrees. So below 120 degrees, there is no thigh calf contact, but then it increases. Okay, and it's about 34% per leg. So that is 70% in total. So we know how much the force is, and we know the distance from the knee, because we can measure that. Okay, the center of pressure. So we can put it now in the model. You can imagine that. So we put it now in the model and see what it does to the forces in the knee. So what we have is now here the force in body weight in the knee and the thigh calf contact, the force during flexion angle. Okay, and what we see here is this force is only this is per leg, 35% here. This is 35% in black. Very small force, right? Very small force. But because of the lever arm is 15 centimeters and the lever arm here in the knee are very small, this has a huge effect. So this is only 35%, but you can see that this is, for example, the compressive force in blue, 3 times body weight, and if we squat, it's going to 4.5 almost. And if we do not include thigh calf contact, it goes on and on and on. But in fact, if we include the body of the thigh calf contact, it actually goes down because the person is going to sit on the calf. So if you look at how you should analyze a high flex design at let's say 150 degrees, we should use these forces and not these forces. Okay? And of course, no patient is the same. So it depends also, the thigh calf contact, on how skinny you are or how not skinny you are. Yeah? These are, of course, Western people. So you can imagine that we also measure the circumference of the thigh and the calf. And depending on that, we see a very good relationship between the forces, the thigh calf force, which increases if you have an increased thigh calf dimension. That's logical. So we thought, okay, from if you have a skinny patient, we can compensate for that in the model and things. And we never got to that, but it's interesting to have that correlation. Okay, so I've shown you this before. So a stress calculation on the plastic with no thigh calf contact. But with thigh calf contact at 155 degrees, the stresses are actually lower than we thought. So there is an extra safety factor in designing. Then there is often a question, is the range of motion increased after putting in a high flex design? So a lot of people first thought that if I put in a high flex design, the patient will be able to flex further. That's absolutely not the case, because it depends on the person themselves, the characteristics of the person, like the offset that I showed, all kinds of aspects, the thigh calf dimensions. So basically, what is the only thing that matters, at least that's what Professor Ranawat showed. He's actually also from India. He's a very famous surgeon in New York. And he has also designed a lot of implants. The only thing that matters is the preoperative range of motion. That is very predictive. So if you have a very limited range of motion preoperative, postoperative it will be very difficult to get a very high range of motion. So that is correlated. But you cannot expect that if you put in a prosthesis, suddenly the person can bend the leg tremendously. Okay, so in terms of thigh calf contact, it can be large. It affects largely the stresses in the knee. It's about 30 to 35% per leg of the body, 35% body weight per leg. Thigh calf contact considerably reduces the joint forces and implant stresses, and flexion beyond 120 degrees may rarely occur for high BMI, body mass index, so obese patients due to thigh calf impingement. Impingement is contact. So it probably is more applicable for low body mass index patients and the Asian market. That's where the companies are aiming for. Now the next part is about the PCL. We're going to talk about the PCL again. And I show here two components, two designs. This is, you can see here the post, right? So there is a post cam mechanism, so there's no PCL here, but there is a PCL here. Okay? So in high flexion, the PCL becomes even more important because we have to make sure that the femoral component rolls to the back. So you can see that in this animation. So we have the post cam mechanism, and its aim is to push it back. Yeah. And the cruciate ligament, which is connected to the bone, yeah, so it's not connected to the prosthesis, of course, because the surgeon makes sure that the anatomical attachment sites are protected. So it's connected to the bones, to the tibia and the femur, and that also needs to push back the femoral components. So the post-cam and the PCL have the same function. Intraoperatively, the surgeon can assess the tension on the PCL. And if the PCL is too lax, there will be no femoral rollback. Okay? And if the femur doesn't roll back, it will hit the plastic here. So that we call that impingement. Okay? Yeah? So the bone, so this is more anteriorly, we talked about it before, there will be impingement. Okay? There will be no rollback, and here the impingement will occur. If it's too tight, there will be no flexion of the knee, and there will be high loads on the prosthesis. Because if this is very tight, the PCL will be stretched, and then the patient will feel restrained. So you cannot bend your the patient cannot bend their knee. Furthermore, if this is stretched so high, the femur will be pressed on the plastic, and the plastic will see higher stresses. Okay? And we can calculate that again. So we look at different lengths. So a too short length and a loose PCL. And you can imagine if this is too tight, if the surgeon sees that it's too tight, he can use a kind of a knife, and he releases a little bit the PCL so that it becomes a little bit slacker, you know. So he can intraoperatively assess the tension on the PCL, and we call that PCL balancing. He balances the PCL stress. Okay, so we have a very short PCL, a tight PCL, and a very loose PCL. And here we can see the force in the PCL during flexion. Okay, so initially the PCL doesn't do anything. We discussed that already. There is no need. In extension, the PCL is doing nothing. If you bend your knee, the PCL is going to do something. If you have a very tight PCL and you flex until 50 degrees, then the PCL is going to do something. If it's very loose, you can bend further until the PCL is going to function. So here it starts to build up force, and you can imagine that if it's very tight, it builds up a lot of force in the PCL because it's just too tight. If it's too loose, the PCL doesn't function, let's say, until 90 degrees, and then it doesn't build up so much force. Okay? So it catches earlier when it's very tight in flexion. And it generates more force if it's very tight. If we look at the stresses on the plastic, and we have a very tight PCL, we can see this curve. So during flexion, you build up a lot of stress. Yeah. If it's loose, you build up this stress. Okay. So it is much lower. I draw this curve now. This curve shows a non-high flexion design. And it shows how the plastic is digging into the plastic. So suddenly we have a very high stress on the plastic. So these are all high flex designs with a tight PCL. It's still better than a design that is not made for high flexion but digs into the plastic. Okay? Okay. So if I look then where the contact is in the tight PCL and in the loose PCL, we can see that the contact is more on the back with a tight PCL than with a loose PCL. And so the tight PCL pulls the femoral component to the back. Yeah? So it does its function in terms of pull back, but it just generates too high stresses. So that's not good. And we call this case is a well-balanced PCL. So there is a kind of, it's in the middle, let's say. If the PCL is very tight, you can even have plasticity in the plastic. So it deforms plastically the plastic. So that's not what we want. And in the simulations, what we did not consider is that even the PCL could be damaged. We didn't consider that. In the simulation, we just assume that it remains intact. What is also sometimes reported is that you have lift-off. So if this PCL here is pushing the femoral component very hard on the plastic, you can sometimes see, the surgeon see that the plastic is coming off on the front. We call that booking. Okay, so then he knows that the PCL is too tight and he will do a release. Yeah? Okay. If we look at high flex designs, there have been some clinical studies, and this is a study from Korea with an implant. It's called the LPS Flex, so that's especially made for high flexion, and it's being sold by Zimmer. And they reported 38% loosening after less than 3 years. That's huge. That is really a big problem, huh? Because nowadays, after 10 years, we have a 90% survival. So there's something wrong here. And they say that the loosened knees were associated with higher flexion ranges and weight bearing in maximum flexion. So the persons that used really the implants at high flexion, they were squatting and active, they failed. And I have to say that there are only a few studies that have reported loosening of these implants. So it's not that bad also. But they have an X-ray that shows like this. So this is the early post-operative, and this is after 32 months. What you can see is that here is loosened. You can see that here. So the femoral component is just loosening. And from a mechanical point of view, we can analyze that. So we did. So what you see here is the interface between the implants and the cement. Because you can see here that it's loosened, so the interface strength is not adequate. Okay? So it was a cemented device and the cement strength was not good enough, so it just came off. So we calculate here the tensile stresses at the interface, so how much it's tense, we pull apart, and we calculate the shear stresses, because that both leads to failure. Okay? Well, we see that the tension is not so high, and we calculated that for 120 degrees, 145 degrees of flexion, and 155 degrees of flexion. In our model, you can imagine that we can calculate that, okay? The shear, we calculated also for the same flexion ranges, and we can see that the shear is at the flange, this is the flange, the front, and also at the back, yeah? Okay, so what we also see is that at 155 degrees, we see lower stresses, and that's because of the thigh-calf contact that we now included. Yeah, so 145 degrees is the most dangerous case in our situation. So we see loosening here, we see loosening here, we see also high stresses here and high stresses here. So I think we have quite a good explanation for why it fails, because the stresses are too high. And I think that the designs that we currently have are have a very low safety factor relative to the very high forces that patients apply when they do high flexion exercises. So we need to improve on the designs. That's what I think. So there is room for improvement, and something for you to look at. So this is my last slide. So we looked at the functional analysis of TKA patients. You can do that in many different ways. And I showed you an example of standing up from a chair. We looked at fluoroscopic analysis and how you can see the kinematics of implants and maybe explain differences and different behaviors of two implants. We looked at the patella tracking that is very sensitive and systematically changed by the designs that we currently have. And we looked at high flexion total knee replacement, and I think we can conclude that we need higher factors of safety for these high flexion designs. Thank you. Difficult? It's difficult, huh? It's a lot, huh? But I think when I look at you, I think, no. Good morning. This presentation is about cementless total knee fixation. So we're going to look at how a surgeon can fixate a total knee replacement without using cement. And I want to acknowledge my co-authors on this paper, and especially Sanas Bergmani, and she did her PhD on this project. So this is basically all her work. We're going to look at these aspects. So we're going to look at finite element analysis, and we're going to look at some cadaver experiments. Because typically we would like to combine that to make sure that our finite elements analysis are validated and telling something about what happens actually in the body. So cementless total knee replacement is the fixation of this implant to the bone without the use of cement. And the idea is that the bone grows into the rough coating on the backside of this component. And in this presentation, I'm only going to focus on the femoral component. Okay? The surgeon has to hammer on the femoral components on the bone. And that's it. Then it has to clamp, the femoral component has to clamp on the bone, and that clamping force needs to be high enough to allow the bone to grow into the rough coating. Yeah? So the surgeon will use implantation force and will press fit the component on the bone, which causes primary stability. So primary stability is how stable, what is the clamping power of this component on the bone, okay? So there's no clamping power in this case. Yeah, you can take it off easily. But you can imagine if you make the bone a little bit bigger, the surgeon has to really hammer it on, okay? And then it clamps itself on the bone. Okay, that's what we call press fit. It generates press fit forces. It will create, therefore, stability, and it will allow bone ingrowth in the rough surface, which we need for long-term fixation. Okay? So primary stability is probably depending on the bone quality, on the surface finish of the component on the backside, on the implant design. Maybe you can use some pegs. Like here you have two pegs, right? Can you see that here? So here I have two pegs. And you can imagine that that helps with the rotational stability. Yeah. And the interference fit. And an interference fit is that the bone is slightly bigger than the implant. So if I make this dimension 2 millimeters bigger than the implant dimension, the interference fit is 2 millimeters. Okay? Maybe we need 4, maybe we need 1. How much do we need? Maybe that depends on the design. Maybe it depends also on the bone quality. Maybe for an osteoporotic patient, we need maybe 3 or 4 millimeters. And with somebody with very hard bone, very good bone quality, we need only 2 millimeters of interference fit. It's very difficult to determine what you need to do. Okay, so the primary stability, we can measure that as engineers. We can measure that by pulling it off, because then we know how much the clamping power is. Okay, so the surgeon hammers it on, and then we pull it off. And if the pull-off force is high, there was good primary stability. And what we can do is we can look at micromotions. And the micromotions, I mean the motions between the backside and the bone. Because if the motions are too big, it means that the bone will not grow into the coating. You know, it will, because every time a small piece of bone has grown into the coating, there is going to be motion, and that ingrowth is let's say, damaged. Okay? So primary stability can be quantified in terms of micromotion and pull-out force. That's also what we're going to use here. Okay, so I told you we do finite element analysis and cadaver experiments, and I will show you 4 types of research that we did. Okay, so we start with some finite element analysis. And we did a very simple test, which is a sawbone block with an implant, okay? And the machine can push it on and can pull it off. Very simple, yeah? And we looked at different interference fit, so between 0, so that means that the cuts are exactly the same as the inner dimension of the implant, yeah? We look in the simulation at different friction coefficients between 0.5 and 1.4. Nowadays, companies can make coatings that have really very rough surface and friction coefficients beyond 1, so that's very good. And we can look at different foam stiffnesses of this foam block because there are different grades. Yeah, and we simulate the pull off. Okay, so it's a very simplistic model, and you can already guess what we found in this simplistic model. So if we have an interference fit which is bigger, the forces here will be bigger, so the pull off will also be bigger. If the friction coefficient is bigger, it will be more difficult to pull it off, also bigger. And if the foam stiffness is higher, the forces will be bigger here as well, because there is more resistance. Pull off will be more difficult. That's very logical. And it's also what we found in this simplistic model. So the pull out force was increased by increased surface finish or friction coefficient, better foam quality, and a bigger interference fit. Now, that is very simple, but it's a foam block, and bone is more difficult. So we go into a cadaver experiment. Excuse me. So we do a cadaver experiment, and of course the different cadavers will have different bone qualities because we are depending on the donors that we use. And in the bone we have different bone mineral densities as quality, but also there will be stress relaxation. Yeah, we talked about it before, but stress relaxation is, so you put it in and there is going to be a lot of force. So if there is an interference fit, there's going to be a lot of force, yeah, because the surgeon hammers it on. But if you wait for a very long time, the stresses gradually disappear, okay? Because it's a viscoelastic material, bone. But we don't know how fast that goes, and whether it depends on the bone quality, we don't know. So the surgeon might think, oh, I hammer it on and it's, you know, very solid. But if these pre-stresses disappear within 15 minutes, yeah, it doesn't tell the surgeon anything anymore. So we need to know that better. So bone quality is important. The surface finish, we looked at 2 surface finishes. One is the poro coat, which is already clinically used by Johnson & Johnson, and a new coating, which is the advanced surface morphology, which is super rough. And it has a friction coefficient beyond 1. Okay, it looks like this. So this is the back side of the femoral component. You can see very nice, very rough surface, and the bone should like this surface to grow into, because then it fixates the component. Yeah. Okay, so of course we are going to look at how implant force is related to the primary stability, because that's what we want to know. We're going to look at whether implant force is affected by the bone mineral density and the surface coating, because you can make it super rough. If you make this, really very rough, maybe the surgeon cannot hammer it on. So, or it is so rough that it's malpositioned. So there is, of course, a limit to everything. You cannot have an interference fit of 1 centimeter because then the surgeon cannot, it's impossible to put it on. So it could also be that the alignment of the implant, the alignment that we talked about, it needs to be aligned according to that mechanical axis of the hip, the knee, and the ankle. It needs to be very straight. If the surface coating, for example, jeopardizes that, that's not good news. Okay, so first we're going to look at how implant force is affected or affects the primary stability. Then we're going to look at surface coating and bone mineral density. And then we're going to look at bone mineral density and bone stress relaxation and surface coating. I will go over them. Okay, so we have 9 pairs of human cadaver femora, and we have always all donors, which is a limitation because the cementless components that you see here are usually used for young patients because the young patients have better bone quality, and that's the selection of choice by the surgeons. If we do cadaver experiments, we are left with older donors, so it's not it's not optimal, but there's little to do about it. Okay, so we ask the surgeon to make the cuts, and we put on the sigma cruciate retaining femoral component. Okay, the sigma cruciate retaining. So this is made by Dept, which is a Johnson & Johnson company. Okay, then we wanted to know something about the bone quality, and we thought long about it, what we should measure then. What is bone quality? That is a very complex question. So you could consider the whole bone, but we decided to measure the bone quality where it matters. So, of course, the clamping force is provided particularly at these sites, at those sites, right? That's where the clamping power is coming from. So there in that region, you want to know the bone quality. We thought if we measure the quality of the whole bone, we might not have the local information that we really need, okay? Because it then diffuses the information. So we took 2 regions of interest to calculate the bone mineral density. And we took that a little bit from finite element models, so because we calculated the region where the stresses were high because of the, let's say, the clamping power of the implant. Okay, we also wanted to measure the dimension, and that dimension determines the interference fit. If this is much larger than the component dimension, the interference fit is large. If this is smaller than the component dimension, there is no interference fit. I mean, there's a negative interference fit, there is no holding power because the bone is just too small. Okay, so we determined that simply on CT scans. Then we wanted to know something about the bone stress relaxation. And it's very difficult to do that, but we thought we could measure that by applying the component on the bone and measure the deformation of the components. And then we measure that by using strain gauges. Okay, so it means that if you put on this implant and the bone is big, it means that this will deform a little bit. It will open up a little bit. And strain gauges are super sensitive. And we can measure from the electrical resistance the opening up of the femoral components. Yeah? So it's kind of like a spring. So there is now force built in the femoral components, and if the bone then relaxates, it will release, the spring will go back and the femoral component will go to its original dimension, and we can pick it up by the strain gauges. So that is how we can pick up the viscoelastic behavior of the bone. Okay? Because you cannot measure it directly. I think it's impossible, but if you have ideas, I would like to discuss that with you. Okay, so we can measure this force by measuring the deformation of the implant. If this force disappears in time because of viscoelastic behavior, the implant will spring back, and we can measure that. Okay, so what we did is we used the machine to insert the implant on the bone. Then we let it rest for 30 minutes to see what the viscoelastic behavior was. Then we loaded the implant dynamically, a little bit more on the medial side than on the lateral side, because that's typically more load goes through our medial condyle than the lateral condyle. Then we had a resting period again, and then we pull it off. We pull it off, and we pull it off because it simulates a little bit the high flexion. This simulates like kneeling or squatting, a deep squat, that the forces tend to push off the component from the bone. So this generates a measure of stability. So this is then a typical strain gauge measurement. So the machine, so we start with 0 strain. The machine pushes the component on, and we see a lot of deformation of the component, and then the machine is releasing the component. So this is the built-in strain in the component, and that's due to the interference fit with the bone. Yeah. Then we wait for 30 minutes, and we lose a little bit of strain. Then we start dynamically loading. You can see that also during loading we lose a little bit of strain. Yeah. So this is the initial strain. This is the first resting period. This is dynamic loading. This is the second resting period, again 30 minutes. And this is then the residual strain after resting, loading, and resting. Yeah. And this is then the stress relaxation. Yeah. Or strain relaxation, I should say. And this is because of these forces are reducing. For the alignment, that was quite difficult for us, but for the alignment we looked at the angle between the bone cut and the dimension, the design of the implant. You can see that there is a small degree of malalignment here. Yeah, and ideally the surgeon wants to have this flat on. This should be flat on. This is called this oblique cut. So this oblique cut, and here it's called the chamfers. That is not so important, but the surgeon absolutely wants to have it flat on here on the distal part. The chamfers are less important, and there are even designs that assume that there is a hole there, because we want to have here bone ingrowth and very good fit. Okay, so we looked at the alignment in the sagittal plane, but also in the frontal plane. We looked at this gap on the medial and lateral side, and then we could see whether it was out of plane. Okay, so how does bone mineral density affect the implantation force and the fixation strength? And we see here the average bone mineral density that we measured from the CT scan in these two regions that I showed you before. And we have a number of specimens. And you can see that the insertion force and the push-off force are highly related by the bone quality. Yeah, so this is the insertion force. So you need to have much more power if you have good bone quality. So you can imagine that the surgeons select patients with very good bone quality, because then they feel that there is a good fit, that there is, they really have to hammer it down. They like that, because then there is a good fixation. The push-off force was also highly correlated with the bone mineral density by the bone quality. Okay, so does bone stress relaxation depend on bone density? Okay, so how much pre-stress do we lose, and does that then depend on the bone mineral density? Well, we can see here, we have not many cases of course, but we can see here that there is a strong correlation between the bone mineral density and the loss of strain. So you can see here, if you have good bone, you do not lose a lot of strain. So that means that if you have osteoporotic bone, you have a lot of difficulties of getting it clamped in the first place. And while after you have clamped it, there is a lot of stress relaxation, so you lose extra. Okay, so for osteoporotic patients, first the clamping force is limited, and that is lost quicker than in a very good bone quality. So there are two phenomena amplifying each other. So that was very interesting. I had not expected that, but after, in retrospect, this seems logical. Okay, so what is the relationship between implantation force and primary stability? So of the implantation force that the surgeon would feel and the push-off force. If that is not related, the surgeon might have the wrong feeling. But luckily, there is a very good correlation. So if the implantation force, insertion force is high, the push-off force is also high. So the surgeon can feel during implantation, this fits very good, and then it's also very difficult to remove, even if we include the bone relaxation. Is there a relationship between residual strain and the push-off force? Yes, there is, of course, because if the clamping force is higher, it's more difficult to pull it off. And you can see that here. It's a very nice correlation. So that makes sense. What about the two roughnesses that we had? We had a very rough surface and a moderately rough surface. During implantation, it is slightly more difficult to implant the very rough surface implant, but it was not significantly different. When we pushed it off, there was a bigger difference. So this was statistically significant. So the advanced coating clamps better, has a better fixation than the traditional coating. We know that this works, and that's clinically already proven. So the chance is very good that this certainly works. And for a company, that's of course very important. So this is a typical thing. We compare something, we compare new things with something that already works. When we looked at the alignment, this is in the sagittal plane, so this is in this plane, we basically didn't see anything. So the angles were very small. It's only 2 degrees, so that is within the 3 degrees. I told you the day before yesterday, the surgeon wants to orient everything with an accuracy of less than 3 degrees. This is less than 3 degrees, so no problem there. And in this plane, the coronal plane, so that is this plane, yeah, it's even smaller. So it's within 1 degree. So we didn't see anything. So there's no effect of the coating, no problem. So let's say the conclusion of this part is that the implantation force is related to the fixation strength. That the bone, if you have a bigger bone quality, a better bone quality, the implantation force is higher, the fixation strength is higher. So bone quality is very important. And if you have a better bone quality, you lose less strain. Okay? Okay, in terms of the advanced coating, we only saw that it did something for the push-off. So that's good news for the company. For the alignment, we didn't see any effect. And for the implantation force, we did see a little effect. And you can read this paper, and I can give it to you later, because Sanas published this. Okay, so we're going to look now at a finite element analysis, and we are interested in micromotion, because the micromotion determines whether it's going to be ingrowth locally. And we look at different activities and different implant designs. So here you can see what we're going to look at. So we're going to look at the motion between the implants and the bone. And if this is smaller than 40 microns, There's going to be bone ingrowth that is being assessed in animal experiments. If it's bigger than 150 microns, there's going to be soft tissue formation. That's the kind of a general limits. You can imagine that if you put on here a type of coating, or you can add maybe cells or medication, then these limits change. But in general, this is what people would use. Okay, and we're going to look at two different designs. It is the Sigma and the LCS, the low contact stress. And these are two designs which are sold by Johnson & Johnson. And they are very similar, slightly different. Okay, so the research questions were: how are micromotions affected by doing a gait or a squat, during gait or a squat, bone stiffness, and by these two implants? How does it work out? So we generated a finite element model, and we do that by making a CT scan. And I told earlier that we use a calibration phantom in the CT scan, and you can see the calibration phantom here. So these are 4 tubes with different calcium equivalent values that allow us to compensate for artifacts in the CT scanner to a certain extent. There are more problems, but we know at least the calcium equivalent values in the bone. That's how we do it. And we segment the bone and make a finite element model of that. We simulate the bone cuts, yeah, and then we have the bone model. And you can see here the bone mineral density distribution. So here you have cortex, which is high, and in the distal area it's lower, because it's more cancellous bone here. It's lower in stiffness. And then we varied the bone mineral density plus or minus 30% to assess the sensitivity of the micromotions of a good bone quality or not such a good bone quality. So we artificially simulate that, not by using all kinds of different bones. Yep. So these are then the models that we generated. This is for the Sigma and this is for the LCS. So you can see here the metal component, and you can, people who work with finite element models immediately see that there is a denser mesh here and here, so it looks a bit strange. And we did that because we know that here in this area the patella forces are going to be applied, and for the LCS it is in a different location. And we decided to use that information to apply the forces in exactly the same location as where people have measured that. And that's why it's a little bit different. Okay, so you can see here that we applied forces. So there is this is during gait, so you can see here basically the resultant force during gait, and also the patella femoral force is here, yeah. And we obtained that from the people in Denver, from Paul Ruhlgutter and Claire Fitzpatrick, because they make musculoskeletal simulations. You can see that here, of gait and a deep knee bend. And they got they validated their musculoskeletal models based on cadaver experiments, which they fed by measurements done in Berlin. So in Berlin, they measure forces in the knee using sensors in the knee implants. I'm going to tell something about that tomorrow. So they know exactly what forces are generated during gait and a deep knee bend. They put that in a cadaver jig, and they simulate then in their model the jig. So they validated then the model, and then they simulate the gait and the deep knee bend, and that's how we get the forces. Okay, this is also an example how you can collaborate with other groups, because you do not have to do everything yourself, because it's very difficult to do everything. Okay, So then we are interested, the outcome is micromotion. Huh? So we have now forces, and now we want to quantify micromotions. And then I got really confused because I don't know anymore what a micromotion is. Because you can imagine that if you have a load and you unload, it's very simple. It's a load and unload. It's just this motion, right? This is clear what a micromotion is. If you have a gate or a deep squat, the micromotion is going to be something like this. You know, it's going to be a curve. So now we have to quantify what we use as a measure of micromotion, and we decided to have the longest traveled distance. So this is going to be the micromotion. But I think you can, from a scientific point of view, you can also say, okay, but we also need to include this, because if this curve would be very long, maybe this would also be interesting. So there is a lot of work to be done here as well. Okay, but at least this is now the micromotion that we assume. So we're going to look at all these aspects and see how it does to micromotion. We start with gait and squat. And we project then the micromotions that we calculate on the components. And during gait, we see micromotions occurring in the flange. This is on the anterior side. This is gait and this is squat. So you can see during squat, these micromotions are bigger than 40 microns here. So during squatting, it's more challenging that there is ingrowth. Yeah, and that complies with what we discussed earlier about high flexion design. So squatting is just more challenging for a design. It's more challenging for a cemented design, but also for a cementless design. Okay, then we look at bone stiffness, and we have here the minus 30% and the plus 30% quality. And we look at the micromotions, and we see, I was a little bit disappointed. We do not see a lot of sensitivity to the micromotions. Yeah, and this is during a squat. So apparently it's less sensitive in the model, at least, than we thought. Then we look at implant design. So we have here the sigma for squat and gait. We have here the LCS. And we see that the LCS has a little bit more motion. Here also motion. Here almost no motion. So the LCS produces more, it's less stable than the sigma. Yeah. Whether it's clinically relevant, we don't know. We only can say that this is a little bit more than this. So what we see is that during squatting we have higher micromotion. Okay. The bone has a minor effect, so apparently bone quality is less of an issue for the micromotions. But we use a very simple bone material model, it's linear elastic. And for the implant design, we see a noticeable effect. In my mind, it means that implant design really matters. Now, you can read this paper, it's just recently accepted in a Journal of Orthopaedic Research. Okay, then we go to the last bit, which is a cadaver experiment. And we're going to look at how bone quality affects motion. We're going to look at implant design. We're going to look at the LCS, which is on the market, but the Attune is not on the market yet. So the Attune is a new design from Johnson & Johnson. It is on the market for cemented, but I think it may be now on the market for cementless, but at that time it was not on the market yet. And we're going to look also at the interference fit. And I told you before that we assess the interference fit with the CT scan, you know, the dimension with the CT scan. In this case, we used an optical scanner because we wanted to be more precise. So the optical scan can scan the geometry . So it means that you have in one cut you can have an interference fit which is different location-wise, you know, because the cut can be curved or something, or not smooth. So it depends, it can locally differ. And we're going to look at a gate and a deep knee bend loading condition again. And we do that with digital image correlation. And Professor Gupta here also has that facility, so I'm not sure whether you can have a look at that. But it's very interesting. So what you do is basically, you have, here we have the bone and we have the components, and we clean it very well, because if it's like kind of wet, it's not working. Then we spray a white paint, and then with a black speckle pattern, you just generate all kinds of speckles on it. Then you look with the camera very locally, and then you can assess how the speckles of the implant move relative to the speckles on the bone. Yeah, and then the disadvantage is a bit that the camera focuses on a very small region of interest, because we want to have a very high resolution, so we look very carefully. So if you want to measure it at multiple spots, you need to move the camera or the specimen, and then look, load it, unload it, and then so you move around a bit. So that's a little bit of the disadvantage. Okay, so here you can see, if we load it here, the implant, you can see that the implant moves and the bone moves, and we're going to calculate now the difference in move between the implant and the bone, and that is a quantification of the micromotion. Because now, from a global point of view, it seems as if it's one rigid body. But actually, what happens is that there is a slight difference. I think you can see it here also, if you look here. It's very difficult to see, But these motions are also in the order of 40 microns. I mean, you can't see that, Okay, so first we look at the optical scanners, and we were particularly interested in zones 3 and 4 and 11 and 12, because these are generating these forces, right? So those cuts. And if these cuts are not made very good, the clamping power will be less or more. And what we saw is that the surgeons undercut it, so they overcut it, they move away too much bone by 0.2 of a millimeter. There is a clamping power, because they aim for, I think, 1 or 2 millimeters, but it's less. It's less than they actually than they think. Okay. In terms of the gait and the deep knee bend, we typically found in the regions of interest at the flange, we found that there was higher motion in the deep knee bends. There is also higher motion at the condyle, the medial condyle, and there is a little bit less motion at the lateral condyle, although there was a lot of variation. With the bones, you can imagine there's a lot of variation. But what we typically found is that during the deep knee bend, there is more motion. Okay? What about the bone mineral density? So, in our specimens, we saw that if you have a better bone quality, the motions were lower. So that confirms what we earlier found. We found this even with the foam blocks. At the beginning of my presentation, we had very stiff bone blocks. We found a higher push-off force. So it's all consistent. Okay, when we looked at implant design, so we have the attune and the LCS. We see here the micromotions for the attune and the LCS during gait. We see here the micromotions during deep knee bend for the attune and the LCS. So what do we see? The attune has lower micromotions than the LCS. The attune has lower micromotions than the LCS, also for gait and deep knee bend. The LCS is already on the market. The attune is going to be released or currently on the market, and it's more stable than what is on the market. So that is good news. So from a preclinical testing point of view, this is reassuring for the company that they have enough data, that this data confirms the stability of that implant. Okay, so we saw that there was a little bit of an overcut, but we didn't see any effect really with the optical scans. The bone mineral density has a significant effect. The implant design also had a significant effect. The attune is better than the LCS. And the loading condition was a bit more complex. It was a bit variable. But in general, we saw that the deep knee bends generated the biggest motion, which makes sense to me also. So this was a very complex presentation. I thought I give you some highlights. So the higher the surface roughness, generally increases stability because it is the friction coefficient is higher. The interference fit is very important for cementless implants. If it's too small, there is no stability because the holding power is too small. If it's too large, the surgeon cannot hammer it on because he will damage then the bone. Okay, I didn't show it here, but that's what we found in other simulations and other experiments. The viscoelastic properties reduce initial fixation, as we saw, especially in poor bone quality. Okay? The implant design does affect stability. The bone quality is important for push-off because we saw that there was a very clear relationship between the bone quality and when we push the component off. But we found a little bit less effects for the micromotions. This is still a bit something that we need to study further. The high flexion loading conditions lead to higher micromotions than just gait. And the models that I showed do not include the complex behavior of bone, so the finite element models. So I would trust in this project more the cadaver work than the finite element work, because what we see is that viscoelastic behavior is very important and damage. So the surgeon can hammer it on and he can damage the bone. So we are now developing finite element models that include viscoelastic behavior of bone and the damage of the bone. And I think with that we get much more realistic finite element models. That's why it's so important to make that combination. And also what we did not include is any biological aspects, of course. And biological aspects are super important for a cementless device. So for example, I know that you could make it very rough. If you have a very rough component, it could work almost as a rasp, on it. And you could say, oh, there is a lot of damage, so that's not good. On the other hand, the rasped bone bits stimulate bone formation from a biological point of view. So you could stimulate bone formation and then therefore actually accelerate bone ingrowth. So of course these models don't include that, but it's very important. So therefore maybe animal experiments or very careful patient follow-up is important to also assess the biological aspects of these new implants. Thank you very much.
Banerjee Chowdhury. He is actually working as the head of the Department of Orthopaedics in AMRI sort of like hospital. He has practiced extensively in India and particularly in the UK. And he specializes in joint replacement surgery and trauma surgery. And he will speak specifically on total knee replacement. And we have been successful in hijacking him from the busy schedule in Calcutta. He almost operates one per day at least. What's your statistic?
3 per day.
3 per day. Difficult situation.
I had to operate 6 yesterday because I was coming here today.
So you should say something about this. Alan, what is the statistic?
Well, I met somebody from India, an orthopedic surgeon, last week.
Yeah.
And he said that he was operating 75 cases
In a week.
in that week, the week before. But of course, he had a team of 12 assistants.
Yes.
So it always depends on what the surgeon does and what his team does.
I think what's happening is that over last 5 years, that the number of joint replacements, particularly knee, has gone up so rapidly that if you consider the whole world statistics, India ranks, there are about 3 centers who are within the first 5 or first 7. So the highest I think is from China. Second highest is from Shalby Hospital, which is in Gujarat. They do about, I think, 20-25 knee replacements every day. And then there's another center in Delhi where they do similar sort of numbers. And Chandigarh is another center where this coming up. They do about 1,100-1,200 joints. And so numbers are going up rapidly, very rapidly.
It also depends, of course, of your clinic. If you have a kind of standard patient category, or if you're more in an academic center, you get difficult cases.
You're right, but in India, what happens is that people don't opt for surgery as soon as you offer them. So what happens is that we usually get the slightly more complex than usual routine what you will get in Europe or in the States. So cases are difficult, but these high volume centers, yes, they have to do it, and they have a better center. They have 4 OTs, they have 4 teams operating. The surgeon just goes around, I'll show you in the lecture how it is done, so you would have an idea. They would do the ligament balancing, do the implants, and then come out, go for the next one. And the rest of the team sort of manages the surgeon.
So what will be our reason for increasing this number of operations from last 5 years?
See, if you look at the demography, Asians get more of knee problems and arthritis. Europeans, Caucasians, they get more of hip problems and arthritis. In our sort of scenario, it's that the awareness is going up. Awareness is going up that knee replacement works. Secondly, people are living longer. We are unfortunately, or fortunately, I don't know, that we are going into nuclear family sort of setups. So the initial, if you look at 20 years back, people had help at home or had support from the rest of the society. That's not there. So people are sort of now concerned that they have to be well to manage themselves. And thirdly, that economically, I think we have improved a bit. So dishing out 2 lakhs of rupees once you are 60 is not a major problem for a middle class family. And obviously Mediclaim and insurance and all these things, they are supporting as well. So overall, people are accepting the fact that yes, we'll go for surgery. That's why the numbers are going, because we have a huge middle class and we have a very rapidly increasing old age population as well.
Okay, so when you were extremely grateful that you could make some time to
My pleasure, my pleasure.
This program, and we are looking forward to a lively presentation.
Thank you very much. Thanks. First of all, I have to say that when Sanjay called me up last week and said that I had to do a presentation talk for 2 hours, I was really taken aback because we are not used to talking so much. We don't take classes. We are not in the academic sort of like. So, but however, I have tried to sort of see how you feel, and because it's a sort of close group, I would suggest that whenever if you get bored or if you have any questions, just let me know. We'll stop and start again.
Here, is that since it is recorded live,
Also, we can stop.
you can't stop.
Right.
So when you stop, then you can have the interaction.
Okay.
And then after say 1 hour, we can stop.
Sure.
And then after that,
Sure. Okay.
after the recording is complete, the presentation is complete, you can have it.
Okay.
If you want to have 45 minutes,
Yeah.
1.5 hours, if you prefer, it's fine.
Sure. Let me see how it goes. Sanjay, have you got a pointer? They'll see it on there, no? Okay. So I'll use the mouse. Okay. All right. Right. Morning, everybody. As I said before, that this would be a very, I would like it to be a very interactive type of thing. And if you have any questions, just keep them for when we have the break, we'll discuss them. This is the hospital I work in. This is the building. This is AMRI Salt Lake Hospital. It is a 250 bedded hospital, and I run the orthopedic unit. I manage the orthopedic unit. My special interest is joint replacement surgery. I do hip and knee replacements both. I've got a team of other orthopedic surgeons as well, and we look into each of us have a special area of interest, and I look after the joint replacement service. First of all, thanks to Sanjay. Sanjay has been very kind to have invited me for this session. I told him that this is more of, we are not academicians and we are not used to giving long lectures or going to the depth of the subject, but he insisted that you will do well. So thanks, Sanjay, for giving me this opportunity. And I can recall from our student days that IITs were the most glamorous sort of places where you could go to. And IITs were the most glamorous of the places you could go to. And you had to be really brilliant to crack those subjects. And I'm sure all of you are. We are not like that. And coming and sharing a dais here is like a dream come true. This is my first trip to IIT Kharagpur. I've never been here before. And coming like this is really a dream come true for me. Now, what I have planned is that our workshop, what I'll do is that we'll discuss a bit about the functional anatomy of the knee and how to approach the knee. We'll talk a little about the signs and symptoms, otherwise it will be very boring. We'll talk about knee replacement as such, the procedure, and then we'll go on to talking about, then we'll start talking about the materials, the components, what we use, and the results of knee replacement. And lastly, we'll touch on what are the advances or where the future is taking us to. And obviously, all good things in life have some problems associated with it. So we'll talk about the problems as well. This is the basic anatomy all of us have to know. If you look at the knee joint, this is the lower end of the femur, and this is the upper end of the tibia, which is the leg bone. and this comprises the joint. However, there is a small bone in front of the knee, which is called the patella or the kneecap. All of these three bones are comprise the knee joint. It's okay. Yeah. Comprise the knee joint. So this is the lower end of the femur, this is the upper end of the tibia, and this is the patella, if you can see from the side. There are two important ligaments, as you can see from the sides. These are outside. This is the one on the inside is called the medial collateral ligament. The one on the outside is called the lateral collateral ligament. And there are two ligaments on the inside. I don't know if you can see it or not. They are the cruciate ligaments. One which is in the front, which is called the anterior cruciate ligament, and one in the back, which is called the posterior cruciate ligament. There are two semilunar cartilaginous structures as well, which we call the meniscus. One is on the inside, which is the medial meniscus. One is the on the outside, which we call the lateral meniscus. Now, if you think of or recall all the knee injuries that you have heard about, that usually the young athlete or the footballer, they are out of service because of knee injury. And most commonly what happens is that either they injure the meniscus or they injure the cruciate ligaments. Now, I'm not going to go into the injury part. We are talking about knee replacement. That is our focus. So we'll talk about the diseases, what will cause damage to the cartilage. The lower end of the bones, they are covered with cartilage, which sort of gives a smoothened surface and causes less of friction. Now, in arthritis, which is natural wear and tear, osteoarthritis, the cartilage layer wears out. And it wears out to an extent when it's completely gone and the patient is suffering. That's when you need to go and replace the joint, which we call the total knee replacement. So if you look into the ligaments, that the two ligaments which are most important if you have to perform a knee replacement are the medial and lateral collateral ligament, which will give you stability to the joint. You can take the ACL or the PCL away, that's not a problem, but the medial ligament and the lateral collateral ligament has to be intact. The medial collateral ligament, as you can see here, it stabilizes the joint and prevents the knee from buckling inwards. And while the lateral collateral ligament is required for stabilizing the knee on the outside of the joint. So these two ligaments are very important. If you look at the anterior and posterior cruciate ligament, the PCL is the more important one, which helps us for our normal knee function. It prevents the femur from sliding forwards on the tibia, from the tibia, and also it prevents the tibia from sliding backwards from the posterior border of the femur. And it also helps some rotation of the femur and the tibia, which will give a bit of more flexion or bending of the knee joint. So PCL is very important. And the ACL resists anterior translation of and medial rotation of the tibia in relation to the femur. If you look at this picture, this is an arthroscopic view of inside the joint. This is the ACL. This ligament is the ACL, which runs from the front of the tibia into the lateral inner surface of the lateral condyle of the femur. And the PCL fans from the medial surface of the inside of the femur down to the back of the tibia. So these two ligaments are the inside the joint, and the two medial and lateral collateral ligaments are on the outside of the joint. Next, we come to the quadriceps and the hamstring muscles. They are they also help the knee to function. If you look at the quadriceps, these are the muscles which are in the front of the thigh. And as you can see here, it's quite well defined. There's a group of 4 muscles which are in front of the thigh. The patella is a sesamoid bone. It's a bone but it's inside the tendon of the quadriceps. So whenever the quadriceps is moving or contracting, that the patella moves as well or glides along with the contraction. The quadriceps extends the knee, that straightens it out, and it also flexes the hip. So if you think about straightening your hip, you will always see, if you stand and try extending the knee, you will always see that the hip is slightly bending, otherwise you can't do full extension. The quadriceps helps in that movement. And hamstrings are the ones which are at the back of the thigh. The hamstrings helps in bending the knee, which is flexion of the knee, as well as it extends the hip joint. Okay, these are also important for a normal functioning knee or TKR. Now I'm a clinician, so the talk will be very sort of clinical biased. So don't get me wrong, but as engineers, we also need to sit down and design and talk and discuss what the problems are and things like that. But I think that from engineering point of view as well, you need to know a lot of clinics of how the knee functions and what is expected from the patient so that we can design it together and design it better. So the talk will be biased. So what is the issue? The issue is that about 40% of people who are over 70 years of age suffer from knee arthritis. And 80% of these patients with knee arthritis have some degree of limitation of movement, and about 25% of them won't be able to perform their daily activities. So it's a significant problem, and with our growing elderly population, that this is a huge bulk of patients that we have to deal with. And overall, if you have this kind of situation, that it decreases the quality of life. And as I was mentioning before, that because people are living on their own these days, you have to have a proper health to function normally. Otherwise, you will get stuck. Otherwise, you will get dependent on people. If you look at the prevalence of knee pain, about 100,000 people would, above the age of 55, would have knee pain, but not all of them would need a knee replacement. It's only about 2% of this population who would need total knee replacement, in whom there is extreme disability, in whom there is pain, deformity of the knee, and limitation of movement. If you consider India, there are about 7 crore Indians who are suffering from knee-related problems these days. And if you consider 2% of these, then you can imagine the huge bulk of patients who are waiting to have their knees replaced. And women, they have a higher incidence of osteoarthritis than men, and the ratio is about 3:1. And women undergo TKR much more than men because they suffer more. And secondly, there is evidence that if mother has knee replacement, daughters have a higher incidence of getting knee replacement as well in their family. But it's not a hereditary disease, it's natural wear and tear, and it happens so easily, commonly, that we could think that it's running in the family. Now, what are the characteristics of knee OA? The patient would come to you complaining of pain around the knee joint, and a common complaint is that in the morning it's very difficult to get out of bed and the knee is very stiff. This morning stiffness is typical of osteoarthritis. People who have inflammatory kind of joint problems like rheumatoid arthritis or SLE or other kinds of problems, they would complain of some swelling in the joint, which is joint effusion. And joint effusion is that the joint lining, they produce more fluid in the joint, trying to cause some, it's a sequel of an inflammatory reaction. It tries to lubricate the joint more, and that presents as a swelling inside the joint. There can be thickening of the synovium as well, which is the joint lining, because of the disease process, and this is called synovitis. So if patient who has got synovitis would also complain of swelling in the joint. And if it progresses to night pain, that patients do complain of night pain, that they can't get sleep or they're woken up by pain in the knee when they try turning in the bed. Those kind of situations, you would know that the knee is a lot worse and they would need some surgical intervention. And these symptoms of osteoarthritis, they interfere with normal sleep activities such as walking, dressing, and dressing. What would you find when we examine the patient? If trying to moving the joint, flexing, moving the joint, you will hear some crackling noise, some crepitus. You can also find if the arthritis is advanced, that may have progressed to damaging the ligaments. You may get some buckling, signs of buckling. And there would be tenderness on pressure because the cartilage areas are damaged. This is a post-replaced knee, so don't look at that, but imagine it's a normal one. That this cartilaginous area, if you keep pressing it, there is tenderness around that area. And secondly, because of the synovium covering, which is diseased, it may be tender as well. And as I said, joint effusion is a common presentation. And also if it's a quite advanced degenerative process in the knee, you will see some malalignment, that the knee will be bow-legged, which we commonly see around us, bow-legged, and maybe there could be some joint instability as well. Now, what are the X-rays? To diagnose arthritis or to plan a treatment for arthritis, most of the time a simple X-ray is enough. What you do is that you take a weight-bearing X-ray. It's not like the patient sitting on a examination bed or an X-ray table or sort of sitting or lying there. It has to be a weight-bearing film that the patient would be standing, and then you take the film. You take one anteroposterior view, that's from front to back, and the other one would be not this one, this is an anteroposterior view, and the other one is from the side. Okay, so see the side profile. So one view would be like looking from the front, and the other one would be looking from the side. That will give you enough information of what the knee is like. If you look at this X-ray, this is a relatively, there is arthritis, but this is a relatively healthy knee. That you see, this is the lower border of the femur, this is the upper border of the tibia, and this area what you can't see is the cartilaginous area. So it's well preserved. And if you consider the other knee, that you can see here, that you can trace the lower end of the condyles of the femur, but you can't see the black area here. So the whole cartilaginous area is damaged. Okay, so in a situation like this, where the whole cartilage area is damaged, you would need some surgical intervention. There's no medicines or anything which is going to work. So X-rays can be deceiving and could be over or underestimate the impact of OA on patient condition, because an X-ray like this doesn't mean that the patient is suffering clinically, that they're not in severe pain or their mobility is absolutely restricted. It's not like that. So you have to combine your evidence from the X-rays as well as what the patient is saying and examining your findings, and then you plan the treatment. So we come on to the treatment part now. Just be patient. I'll take you through the surgery. Don't worry. So what are the treatment approaches? It's, as I said, that it's not that as soon as a patient enters the OT with to a clinic with knee pain would need a knee replacement. It's not that. There are lots of treatment options available, and it all depends on the condition of the knee joint as well as how much the patient is suffering clinically. So you need to, early stages, you can educate them how to use their knee. There are quite a few things you can do in their home or their activity, or walking, climbing stairs, or sitting, not sitting cross-legged, which will increase the stress in the knee joint. There are medicines, there's physiotherapy, but I would concentrate more on the surgical side. So when we offer surgery, and why do we do that? The aim of the surgical treatment of osteoarthritis is to decrease or eliminate pain and to improve function. If you give them a painless joint but it doesn't move, then it's no use to the patient. So it has to be balanced, that their pain should go and they should be functionally recover 100%. Otherwise, the patient is not going to opt for it. And secondly, there are multiple surgical options available, but it's tailored to a lot depending on the condition of the knee joint as well as what the patient wants and the social circumstances as well. So you do the surgery for, depending on the pain severity, to improve their functional impairment, and if you get evidence or see evidence of structural joint damage. Now, what are the options which are available? You can do in a moderate arthritic knee where the patient is painful, having pain, but X-ray doesn't look too bad and the patient is not old enough to have a knee replacement. You can go either for an arthroscopy, which is a microsurgery, just to relieve their pain. You can do an osteotomy, just to correct the mechanical axis of the joint, and so shift the weight-bearing axis so that they'll get from the diseased part to a non-diseased part, so that they'll get better clinically, but again temporarily, because it's osteoarthritis is a progressive disease, that they will get relief temporarily, but in the long run they will get their pain back. And finally, you can do a knee replacement if the joint is enough worn out then you either offer them a one compartment knee replacement, which is a unicompartmental knee replacement, or a total knee replacement. This is arthroscopy. Arthroscopy is microsurgery. You do 2 holes from either side of the kneecap. From either side of the kneecap, you put a camera inside the joint, assess the degree of damage, and with the other portal, you put in your instruments and try clearing the joint. If you look at this picture, this is arthroscopy picture, this is bare bone. So this white bit is the cartilaginous area, this thick layer. So what happens is that this cartilage gradually wears out. Now, when it becomes bare bone, it's bone to bone, which is sort of scratching, and you get a lot of pain. So arthroscopically, what you can see is that there is grade 4 changes, which is bone exposed. There's no cartilage left. But what we do arthroscopically is that we these debris, these cartilage particles which are floating inside the joint, increases the load of the joint. So they get more stiffness, more pain, more effusion. So you clean them out and you debride this area. You get these electric shavers where you burr the area, you shave that area of bare bone, and thereby producing some fibrous cartilage, and their pain settles down. But again, as it's a progressive disease, it will get worse in future. You preserve these ones, this procedure, only for people who are youngish, who are young, who haven't reached the age for knee replacement, or patients who are very symptomatic from their pain, but not agreeing for knee replacement. So you remove the loose bits of cartilage and bone, and you drain the excess of synovial fluid, you drain the effusion. And if necessary, if a synovium is very diseased, very inflammatory, then you do a bit of synovectomy, take it out, and that will give them temporary relief. It's done under regional anesthesia, so there's not to worry if the patient is medically also not fit. You can go ahead and do it. It does not involve any blood loss, and as I said, it offers temporary relief of symptoms somewhere between about 1 to 2 years. But after that, they'll come back with the same sort of symptoms when you have to offer them knee replacement. Now, what is osteotomy? This is high tibial osteotomy. We call it high tibial osteotomy. This has recently, over the last sort of 10 years, I would say it's going out of fashion, because results of unicompartmental or total knee replacements are so good these days that people are not opting for high tibial osteotomy. They would have a knee replacement rather than going for osteotomy. What you do is that this is a typical deformity in an osteoarthritic knee, that the medial compartment of the joint that wears out more. So the angulation is more varus, and the mechanical axis, if you consider the center of the hip joint, center of the knee, center of the ankle, that is shifted, and there's a whole weight is going through that side, and patients are suffering from pain. And the deformity is corrected by removing a triangular wedge of bone from the upper end of the tibia. It can be a closing wedge or it can be an opening wedge osteotomy, and thereby you shift the weight-bearing axis. So if you shift the weight-bearing axis where the weight was going through here, the diseased area, that is shifted more laterally. So the patient gets symptomatically better. And this area of the osteotomy, that they would heal on their own like a fracture healing, and patient would be able to walk or perform their normal usual routine function, whatever they want to, without difficulty. But again, because you are not addressing, or we are not addressing the cartilage issue, which is the main problem, that in 5-6 years time the problem comes back. And one of the downsides of doing a high tibial osteotomy is that when we do a knee replacement, we have to get the axis right. Now, in osteotomy, we have already shifted the axis. So we have to recorrect it and bring it to the normal position. So doing a knee replacement in these kind of situations is slightly tricky. So once all these measures have failed, or the disease has progressed that they won't get better with the osteotomy or the arthroscopy, we go on to doing a knee replacement. Now, if you consider a knee, we call it 3 compartments. The medial compartment is on the inside, the medial tibial plateau and the medial femoral condyle. The lateral compartment is on the outside, which is the lateral femoral condyle and the lateral tibial plateau, and the patellofemoral joint. So these are the 3 compartments of the knee. Now, if you, in a uni, If you have a disease in one of the compartments, you can go ahead and replace only that compartment. That is called the unicompartmental knee replacement. But in total knee replacement, you replace all the 3 compartments, or at least the medial and the lateral compartment. So when would we offer knee replacement? A patient who has failed to respond to conservative therapy, then we'll progress onto, we'll offer them knee replacement. When a patient is having pain at rest, their sleep is disturbed, and with every kind of movement they are groaning and moaning with pain, you need to tell them that yes, your knee is worse enough to have knee replacement done. And obviously with all these things, there would be loss of function. These loose knee prosthesis and knee tumors, these are complex areas where we have done a knee replacement, it has lasted its life, and now it's we have to revise it again. But for our purposes, for primary knee replacement, it is mainly on the clinical signs and symptoms as well as radiological evidence of enough damage that you offer them knee replacement. In unicompartmental, it's only a small part of the knee which is replaced. It's recommended for patients with either a medial or a lateral compartment disease, and there has to be moderate to severe pain and functional impairment. It is intended to relieve pain and preserve function for as long as possible. And when the patients come back with either a loosening of this component, or that the other component has, other compartment of the knee has progressed to arthritis, then you go ahead and revise it to a total knee replacement. Now, this is a component of a uni. This is the femoral component, which goes on the femoral side. And then you have this tibia, which is half of the tibial upper surface, as you can, if you imagine, uni would be on either condyle, either the medial or the lateral condyle. Okay, and on the tibial side, it's only, this is for a total knee, but if you can imagine that it will be half of it, hemi. Okay, so this will articulate with only one area, and that is a unicompartmental knee replacement. This is the prosthesis, what it looks like, and that is what it's inside before closing the wound. That you can see that it's only half of the tibia which is replaced, and this is the insert, the plastic insert in between, and that shiny bit is the femoral one. Okay, so we do a unicompartmental. There are strict indications for unicompartmental. You can't do a unicompartmental in a patient who has extensive disease. These are very strict, that there has to be an adequate motion pre-op, because with the uni you are doing partial replacement and you are opening the knee joint only tiny incision. So you cannot increase their range of movement. So whatever they have got pre-op will be post-op. And a fixed flexion deformity is when you won't be able to extend the knee fully, that the knee would be slightly bent from the disease process, from the degeneration, as well as contracture of the soft tissues. Usually an arthritic knee will be slightly bent, that you cannot fully extend the knee or fully straighten the knee. So if you have a patient who's got this kind of deformity, or fixed flexion deformity, with a uni, you cannot correct that. So no point in trying that. These kind of patients will do better with a total knee, where you open up the joint and then release the soft tissues to get them out to length or correct their deformity. In a uni, the other compartments have to be healthy, because there's no point in doing a uni in a very damaged compartment while the other compartment is moderately arthritic, because in a couple of years time they'll come back for the revision. So it has to be, one compartment has to be damaged, the other one has to be relatively healthy, and both the ligaments have to be functioning. If there is damage in the ACL or the PCL, you cannot do an uni. And obviously the varus valgus deformity, because secondly, one deformity what they get in arthritis is an FFD, and the second is because of unilateral wear on the medial side or on the lateral side, patients tend to go into either varus, which is medial angulation, or they go into valgus, which is lateral angulation. If these deformities are correctable passively, that means that there is less bone loss. It's only the ligament or the soft tissues which are balanced, and that you can address by doing a uni. But if you see that it's not correctable, that means there is extensive bone loss there, then a uni is probably not going to work or fail early. If you look at the femoral design, it is of anatomic shape. It goes in the lower end of the femur, you shape it, correct it, and it's got a decreasing radius posteriorly. Okay, so it's just like a cap which goes on the weight bearing of the femur. It's not the whole area which you are replacing. It's curved asymmetrically in the coronal plane, and the tibia insert is flat except around the intercondylar edges. This will be that. I'll come to the polyethylene later on when I talk about the polyethylene, that usually those inserts, this white bit is the insert. We call this insert. This is made of high density polyethylene. They are usually of 2 or 3 types. One is that you can have an extensively flat design. One is you can have a moderately sort of dished groove, and the other one is a deep dish. Now, the significance of these 3 designs is that depending on your ligaments, that how much you want the femoral condyle of the knee to move on these. In a uni, because you are expecting that the ACL and the PCL are intact, that's why you will have to have a flat design on these. Okay, and again, this is a tibial base plate which is half, which sits in the goes in the tibia. You have the polyethylene insert on top, which is flat, except for the edges, which are slightly curved for the margins of this femoral component. Okay. So Oxford unicondylar knee is we consider a sort of gold standard these days. The results of we try to follow that, emulate that results. If you look at the Oxford results, 92.4% are expected to survive at 10 years. In a joint replacement, success of joint replacement doesn't depend on the immediate success. That a patient after 6 months says, my pain is gone, I'm doing everything what I want to do and I've had a great result. No. Joint replacement, the success depends on how long it survives in your body or how long it goes. So results are usually measured in about 10, 15, 20 years time. So it's difficult to get the data, but we are getting the data of about 20 years now, because the patient has to outlive that time as well. The patient after a joint replacement, if has lived for more than 20 years, then only you can go back and assess whether how's the joint functioning for 20 years. So if for joint replacement, it's a different scenario, that it's always a long-term result which will give you the success story. If you look at the Oxford Uni results, a 92.4% success is at 10 years. And at 15 years, it's about 94%. Now, there is a catch. This might look a bit surprising that 15 years is 94%, but 92.4 at 10 years. Now, the thing is that it's a difficult, doing an uni is difficult. So in unskilled hands or less experienced hands, and in selecting the right patients, there was a lot of unis being done. So initial revision rate was high, but as the designs changed and as people grew more experienced, the results are the results which we are getting now are much better than what it used to be, and it's about 91% at 20 years. Okay, but whatever it sounds like from the results, uni knees has to be targeted for typical patients, that it has to be designed and it has to be offered to patients who have, it's a very strict selection criteria. If you do it in a random manner, your failure rates would be high. So now we come to total knee replacement. Now the ultimate solution for an osteoarthritic knee is to replace the worn out parts of the knee with an artificial joint. The prosthesis that is used is made up of plastic, which is high density polyethylene, and metal, which is placed on either side, either the femur or the tibial side. And this surgery has been used for many years now with excellent results, excellent results, particularly for knees. The hip replacements is the first one which hip replacement came in around early 60s. The modern design are the ones we use, but the knee came in much later. The PFC or the standard ones, what we do these days are in the early 80s, are from the early 80s. Now this is, I wanted to deliberately put this picture that when a building is being refurbished or being made, it looks terrible. This is an X-ray. This will be similar to an X-ray of a knee which you are going to replace. This is a typical sort of degenerate knee. You see the varus deformity, the medial angulation. You look at the X-ray that there is no cartilage you can see. It's subluxing medially. So the ligament on the medial side would be short, while the ligament on the outside, the lateral ligament, would be lengthened. And there is no evidence of any ACL or PCL, or you don't expect an ACL or PCL to be here. You can see from the left side that there is extensive tibial plateau loss, bone loss. So this is a complex sort of situation that the only answer is knee replacement, all of us know, but a standard knee replacements may not work, or you have to be prepared for all kind of eventualities. But this lady, she is in her mid 60s. She's worked all her life, and she's managed to maintain her school with a waddling gait, pain, crossing the overbridge. And then once she retired, she came for the knee replacement, that she wants to live her life now. This is another lady. That deformity was a varus deformity. If you see that the leg is bending inwards. Now, if you look at this, it's bending outwards. This is a valgus deformity. If you remember that last X-ray, it was the medial compartment which was damaged, and then knee had bent medially. But on this one, it's a lateral compartment where you can see that it's quite extensively damaged. There's no cartilage left. So the lateral ligament is quite short, while the medial is lengthened on this side. So these are just two diametrically opposite presentations, but the treatment has to be surgical. And you can well imagine that this lady, she was still somehow managing to walk around inside the house. This leg, the left one, which is more worse, is valgus, while if you look at the right one, it's gone into varus. That's also going into valgus. So, okay. So, what does a knee replacement prosthesis look like? This is the femoral component. This is the femoral component. This is the tibial insert, the high density polyethylene. And this is the tibial insert, which goes in the upper part of the tibia. This is the side profile. You can see it's a J-shaped curve. And this is the insert which goes there. That's again the tibial implant with a peg which goes down into the bone. Now, if you look here, that this is a femoral component. This peg is for going inside the bone to give it rotational stability. If you consider this margin, it's like a J-shaped curve, and there are 6 surfaces on here, 6 cuts, which will go in which you have to make on the bone to put this in, and that will give its rotational stability, as well as it will give smooth flexion and extension. And this area on the anterior flange, this got a groove. This is for the kneecap or the patella to glide against. Okay, this bit goes in the posterior condyle. That is the posterior condyle. This is the anterior chamfer, and this is the anterior margin of the femur, surface of the femur. So that is the way it's got to sit. Okay. This is a nice diagram. If you follow it, it'll give you an idea. This is the lower end of the femur, which is damaged. So you cut it in a X shape and then put the femoral component. This is the upper end of the tibia, which is again quite damaged. You cut it flush, make a peg, and then put the tibial component in. And then you get the insert, the polyethylene, which goes on top of the tibia. And that's your knee replacement. If you have to resurface the patella, you take a chunk away, the worn out part, the intra-articular bit, you remove that, and then use these plastic buttons, which are patellar replacement. You put it in there, and then you put it back on again. Okay. So, and then you always check about the stability and the range of movement of the knee joint, then you have done a good job. So this is a schematic sort of animated presentation of what happens. I'm not going to go into any videos, but this is how the position is, that if you see this leg, which is a typical arthritic, what I showed you earlier, the fixed flexion deformity, that the knee is not straight. Usually all our knees will hyperextend, the knee will go up. But in this one, you can see that there is about 5 to 7 degrees of fixed flexion deformity. And if you see this, that it doesn't go beyond this movement, it's about 70 degrees of movement. So the knee is very stiff, there may be bone deformities inside, what we have to correct surgically. What we do is that once we have exposed the bone, this is the jig which we cut the tibia. If you think of the tibia, I'll use this. If you think of the tibia from the lateral side to the medial side, there is a 3-degree slope. Okay, and the medial side in an arthritic knee, what we are seeing here is quite worn out. So you need to create, once you have that, you need to create a quadrangular space in the joint so that the medial and lateral collateral ligaments will be well balanced and you will have a good stability of the knee joint. So in doing that, you need to consider the 3 degrees of valgus angle, and you need to give it a slight posterior slope on the tibia. This jig is got already built in that slope, and it's designed in that way that you take 3 degrees on the tibial lateral surface and you from the medial surface, the worn out area. Use an electric saw to make a cut like this. It has to be absolutely flush. Once you have done that, then you start working on the femoral side. These are the jigs which we use to cut the anterior surface, which is worn out. You can see that this surface is more worn out. So you take that area out, and then you will have the quadrangular space. Both surfaces, the tibia and the femur, if you consider this, that you will have a quadrangular space if it's balanced and it's parallel to each other, the two cuts. Now, once you have done that, you need to see the balancing of the knee. Balancing of the knee is very important for a knee to survive, and it's the medial collateral ligament and the lateral collateral ligament which has to be well balanced. So what you do is that once you have done these two parallel cuts, then you get these blocks. We call them spacers, 10 millimeter spacers, and you can increase that. You put them in and then see how much of correction is there. If you have this block sitting in between the two cuts quite snugly, that means that the ligaments are balanced. And with these two cuts, if you can get the deformities corrected, then that means your bone cuts are enough. Next, you have to shape the femur and the tibia to put your components in. But if you find that either the medial or the lateral side is tight, it's not sitting properly, then you need to do some surgical release or soft tissue correction to get them out to the normal gap or the normal sort of strength. So once you have done that, this is the flexion extension gap, and you need to check it in flexion as well, 90 degrees of flexion, so that the knee will be well balanced during the full movement. It's not that in only extension you are checking it, you are checking it in flexion as well, so that it will be well balanced knee. Then you go to shape the femurs. These are called the chamfer cuts. That is, you do the chamfer cuts, and then you put it. This is a trial component which has gone in, and you do a box cut, which is this cut inside in between the condyles. What happens is that if you think that this is the original prosthesis, that you have to make space for this box in there. That goes in that groove, and that gives you the rotational stability of the component. Okay, so you do the box cut, and then you do a trial reduction with your components. You need to see the varus and valgus stability. That means that you see that the medial and lateral ligaments are well balanced or not. You see that whether their FFD is corrected, the fixed flexion deformity is corrected or not. And number 3, you see the range of movement. But these are the three things you need to watch. If you are happy with it, then you take your final prosthesis and insert them. This is the tibial preparation, and then you see the, as I said, that you see the alignment, and this is what would look like inside. This is the femoral component which has gone in, this is the tibial insert, and this is the patellar replacement you have done. So once you are happy with this, just reduce it and close it in layers. If you now just try remembering those x-rays where it was in gross valgus or gross varus, that the one of the sides was completely gone, but now after a knee replacement is an immediate post-op picture, x-ray, that you see that the gap is recreated and the both the sides, that these are equal. That means the medial and the lateral collateral ligaments are well balanced. So this is a good knee. You need to see, there's a lateral view, side view. You need to see that the femoral component also going on the lower end of the femur. It's sitting snugly on the anterior cortex as well as the posterior cortex. So the size is right. And you see that this is the upper end of the tibia. You see the margins of the prosthesis. It's covering almost 100% of it. And it's not over, it's not outside the margin. It's not very small. So it's the right size. And also you need to, because you fix them up with bone cement, you see the margins, that the cementing, that it's well cemented in there. There's no looseness or no gap. This is again a side view. You see all around the tibial prosthesis that there is cement and it's sitting nicely. So this is a post-op knee replacement, and a picture, x-ray picture should look like this. And if you have something like this, that means that the knee is well balanced, the knee will have good movement, and the deformity will be corrected. So the patient would do well. Now, how do we manage in the post-operative phase? Main problem in the post-op phase is pain. So you need to control the pain. There are different sort of medications. We do some intra-articular injections while doing the surgery. We do nerve blocks, and they have injectable medication as well as oral medication which controls their pain. Because if they can't control the pain, then their rehab will be compromised. And if you don't do the physiotherapy properly, then these muscles and soft tissues, and it's a new joint, it needs to be taken through the full regime of exercises to get the full movement back. So if a patient is not very comfortable with the knee from pain point of view, they would not be compliant with the physiotherapy, and you will end up with a stiff joint. So pain control is our primary concern in these patients. On the second day, they stand, they bend their knee, and they start sitting out in a chair. They can take a few steps inside the room. On 5th to 6th day, we try them stair climbing inside the hospital, and then they are home. Once they can do that, they can go home. Once they are home, they can independently go to the toilet, they can go to the dining table, they can walk around inside the house. If there are stairs, they can go up and down the stairs. And within about 4 to 6 weeks time, they walk unaided, that's without any stick or walker. And they should be driving. If somebody wants to drive or join office, they should do it after 4 to 5 weeks time. And usually, whatever I say, usually it takes about 10 to 12 weeks for full recovery. After about a month, they'll go back to their normal routine, but however, there will be some discomfort and some heaviness, some stiffness. You need to carry on with your exercises all the while. This is an immediate, it is a post-op patient. This is a 4th day or 5th day, I think, that if you can see the degree of movement in the knee, and you can make out from his face that he's not in pain. Because he's not in pain, that's why he can keep his leg like this. If he was in pain, he wouldn't have been able to do that. So what are the results? Again, now the gold standard of TKR results is about 18 to 20 years time. So if your knee, you have to always compare your results with these. 95% of knee replacements are expected to function at least more than 18 years. And if you consider, if you take patient questionnaire, patient satisfaction questionnaire, then about 90% of them are happy that they have undergone this procedure and it has changed their lifestyle. At 1 year post-op, a range of movement should be about 120 degrees plus. 95 to 100% should survive more than 10 years, 90% survival at 15 years, and 85% survival at 20 years. Okay, so results of TKR, as I said, are so good these days that people are opting, or we are also offering them knee replacements rather than trying out on any other medication. Medicines and those kind of high tibial osteotomy or arthroscopy, those kind of procedures. So TKR is quite a successful operation and satisfactory operation from patient point of view. These are few of the clinical x-rays post-operative. You can see again well-balanced knee on both the sides, medial and collateral. You can see the lateral, it's a well-fitting prosthesis. And again, on the other side, these are the points to look for. And this is, look at this person, that there was a varus knee, it's absolutely straight now. If you look at side view with the full extension, that there's no fixed flexion deformity, is absolutely straight. And look at the degree of bend. If a person can bend it up to here, that means they have almost full range of movement. However, because these are artificial implants, it's not recommended that you do that, you sit cross-legged or squat, because it will wear out faster. Where it is supposed to last you for 20 years, may not last you that long. And you see the degree of movement, that it's the calf is touching the thigh, so it won't bend anymore. Again, another slide, there's no FFD. You can see that the movement is more than 120 degrees. That you can see this is more than 120, again, the calf touching the thigh. This is the kind of result you should get. Look at this person who came down from Delhi to have it operated. He's not listening to anybody, he's squatting, he's sitting cross-legged and does all kinds of activities, but he's very happy. He's very happy. So if you have done a knee replacement properly, you can have a majestic architecture like this. This is the Empire State Building. I didn't want to say the name. That was when it was being built, and this is what's the finish like. So we have to stick to the basic principles, and we have to offer the right kind of surgery to the right kind of person. If you offer it to a very young person, because their demand activity is very high, they may not be as happy with it. But again, somebody who's young and who's got very degenerate knee, there is no point in waiting for telling them that it's going to last 18 years. So don't have it done now, suffer for next 5 years or 10 years and then have it when you are 60. That's not right as well, because a person is active when they are up to about 60, 65. So if that part of their life they are suffering with pain and problems, there's no point in giving them a good knee after 65. So you have to judge it right, and you have to stick to the basic principles of how to do it and what to do, and you have to correct the soft tissues properly. It's not a bone surgery, it's not a bone cutting surgery. Main key for knee replacement success is depends on the ligament balancing. Okay, so now we come to a bit of your domain, what we use and how we use it. Now the components, the components are the femoral, the tibial, and the plastic insert. Now this is the femur, this is the femur, this is the tibia, and this is the plastic insert. Now what we always try is that there are 2 or 3 things what you have to keep in mind. One is that the component design, the component material, and the component placement. These are the key issues which will give you good result or long-term success. So we need to look into each of these carefully and get the best combination out, so that you would have a long-lasting total knee replacement. It's same with the femur, it's with the tibia, as well as with the polyethylene insert. Later in my talk, I'll talk about the material which has been used and the designs. More or less, femoral side is probably solved, or there is not much development, which I think you would be a better person to sort of mention it, that from the femoral component side, there's not much we are expecting. Main concern area is the polyethylene. A long term, even if you have done a knee replacement properly, and even if you have a good result, it is not going to last you. If you take the evidence, it's not going to last you for more than 18 to 20 years. Now, to get a knee for lifetime, you need to develop on these issues. And the areas where we are failing now is that the polyethylene, which is the main culprit, which is wearing out. That in 20 years time, because of the wear, because of the corrosion or the abrasion, that the polyethylene wears out slowly. And these fine particles, they go and cause osteolysis, which is bone damage between the component and the bone surface. And that's why the components loosen out, and then you have a failure. But this takes about 20 years to happen. Now, we have to address these issues. If you consider, we'll come to each of them one at a time. If we look at the femoral component, that what we expect from a TKR. Stop. Oh, 5 minutes. What we expect from a TKR, a good functioning femoral component. The requirements for a TKR is that the axis of rotation is about 15 to 20 degrees, and medial lateral, which is a varus valgus stability, that has to be about 5 to 10 degrees. You need to bend the knee. So how much bend do you need? You need about 65 degrees of flexion to walk at a normal pace. If you have less than 65, then you would be limping or dragging your feet. You need 95 degrees of flexion to walk up and down stairs. Now, comfortably, like a normal person does. If you have less than that, then you have to do a one step. You have to take one step at a time, and about 100 to 110 degrees is required if you have to get up from a chair. You can all see for yourselves that if you are sitting with the knee at 90 degrees, it's very difficult to get up. You have to use a lot of pressure on your hands to get up. But if you bend it, if you go to about 100 degrees, then a lot of pressure is being taken up by the knee. So you can get up easily. So these are the basic requirements what a femoral component should give you. And there is another important area is the femoral rollback. Now, what happens is that if you look at this, I'll just try to fix this. Yeah. Okay. So what we were talking is that it has to bend beyond 120, then it will be easy for you to get up from a chair. That it has to be, the axis has to be right. And rollback is, just look carefully, that what happens is that when a knee is flexing, that after a certain point that the femur and the tibial margins are there. So if you can, if the femur goes back about few millimeters, then your flexion can increase a bit more. Is that clear? If you look at this one, that this is a knee which is functioning like this. Okay, this is in flexion, that you see that the posterior margin of the femur is almost there at around midpoint of the tibia. Now, to get further flexion, if you can bring it back posteriorly, then it will bend more. This going back is the femoral rollback. So if you can have a design which will roll back further, which will increase the rollback, then your flexion would be more. So patient will be more satisfied. So we need to look into that as well. If there is no rollback, then there is a lot of pressure which goes to in the front of the knee, and strength of the quadriceps is reduced by about 30% if there is not adequate rollback. So you will have weakness, or you won't have adequate movement or strength in the knee. You can operate the cruciates or the cruciate ligaments, both the ACL, the anterior cruciate and the posterior cruciate. These are not essential for a knee replacement, because there are two schools of thought. One sacrifices the PCL, the posterior cruciate ligament, as well as the ACL, anterior cruciate ligament, and then does the knee replacement. The other school believes in that the cruciate should be retained, so they keep the posterior cruciate ligament. Anterior cruciate ligament doesn't have much function, particularly to knee replacement. So the anterior cruciate ligament is sacrificed in both these cases, but in one school the PCL is retained, the other school the PCL is sacrificed. Both have their individual thoughts and regarding the sort of functional improvement, but with the posterior cruciate TKR, if you are sacrificing the cruciate, then what happens? One of the functions of PCL, as I showed you in one of the very early slides, one of the function of the PCL is to provide this rollback, the femoral rollback. So if you are taking this off, something else has to provide this rollback, otherwise it won't function normally. So what you do is this, in those kind of scenarios, that the femoral, this projection, the posterior condylar plate has to be slightly more prominent or has to be longer so that it rolls back, it will have some surface to roll on it. Okay, so these are the basic design issues which has to be built in the components, so that we have a good functioning knee. If you look at the tibial, now the femoral one, they are built, they are made of cobalt chromium alloy or oxenium. You can also have oxenium femoral components. I'll talk about oxenium in details because this is a very promising one which has come recently, but usually standard is cobalt chrome alloy with which the femoral component is built. If you look at the tibial, it's a titanium alloy, or you can have a cobalt chrome molybdenum alloy as well, but standard is a titanium alloy. Again, it's design specific, so most of the designs will have a titanium alloy, others will have a cobalt chrome one. The tibial one, because it's a flat surface and it's going inside the bone, you have to give it some stability. Now it can be by a peg which goes in the bone, it can be by multiple pegs, as you can see in the picture. It can be one big one and then multiple pegs. Or if you find there is bone loss and the tibia is not giving enough stability, you can have an extension of this peg which goes down into the bone, and that holds into the medullary, into the isthmus of the tibia, lower down, cylindrical. So because the tibia is a cylindrical one, that it gives you hold there, gives you stability there, gives you rotational stability. And you have these flange cuts as well, these sharp flange cuts which goes inside the bone, and that gives you the rotational stability of the tibia. Because the tibia is sitting on cancellous bone, which is not as strong, that's why you have to give them a lot of elements which will stabilize the component, otherwise it will keep sinking down. And there are anatomic variants as well, that you can have a metal plate which is like this, where this is sitting on it. You can have a very smooth polished tray which will give you mobility of this insert on it that rotates, which is called a rotating platform knee. And you can also have, usually this tibia, I don't think I can take this off. No, I don't think so. This is usually a grooved one where this insert sits, but there is a variant where it is, and these are universal, these are standard sort of medial lateral plateau, both are sort of same size and goes in the tibia. But you can have anatomical shaped ones as well for design for right and left, where because the tibia rotates slightly and because the lateral plateau is slightly smaller than the medial side, these are designed anatomically, that one of the sides will be smaller than the other. And these are all designed, or these designs are being sort of thought over because to give you maximum function or maximum benefit from the knee replacement. Thank you. Right.
Because I tell the truth.
It's just I thought that, see, for me to Right, we are back again. Um, Now we've talked about the tibia. Now we come on the insert. This is the most important thing, which is sort of letting us down these days with for knee replacements. Now material is, this is ultra high density polyethylene. We loosely call it plastic, but it's not really a plastic issue. It's There are many designs from flat to dip dish. If you are retaining the PCL, if you are keeping the PCL on, then you can use a flat dish that it doesn't have to be very grooved or anything. But if you are sacrificing it, then it would be a dip dish. You can, there are have been occasions that we try doing in a youngish patient, we try doing a cruciate retaining one, and once in the middle, if you can see that the PCL is not healthy, you can get away with using a deeper dish. You change it to a deep dish one, and that will give you enough stability and rollback of the knee replacement. Wear particles which come out from this plastic are the major cause of osteolysis and failure long term. What happens is that there are microparticles which from long term wear these come out. There is a reaction, tissue reaction, and then they go and they try settling in the bone cement into the cement bone interface. Because if you think of this knee replacement, see, the bone, between the bone and the implant is a layer of cement. Okay, cement is anyway cause for osteolysis, and these particles will float and go and reside on that area between the cement and the bone, and that causes the loosening. So eventually over a time period there will be loosening of the prosthesis. So we need to take care of this plastic, and we need to develop on this. Now, not whatever we do, all good things in life will have complications. Now, what are the complications like? Clinically, the most commonly what we anticipate is a DVT, deep venous thrombosis, because the knee is being flexed so much and is being taken through. Patients tend to develop a clot in the calf veins. If it stays in the calf veins, it's not a problem. But if it travels to your lungs, then it's a major problem. Pulmonary embolus is a major problem. We take care of preventing it. We give them injectables. We get them out of bed early, mobilize them, move them. But in spite of all our efforts, there will be a pulmonary embolus, and the incidence is about 1 in 300. The patients will have pulmonary embolus. The main concern, the commonest sort of problem we get from knee replacements is infection. In spite of all our efforts, there would be patients who will get infected. World literature says that it shouldn't be more than 0.5%, which is 1 in 200 cases, it shouldn't be. There are centers which report slightly more, but overall you have to be careful. It has to be done in proper OTs, operating rooms. Those has to be laminar flow, which keeps the bacterial count low in those rooms. You have to give them antibiotics, and you have to obviously take proper care with disposable drapes and gowns and all the other rest of it. But in spite of all of that, all our efforts, there will be infection. Fortunately, or touch wood, I've had only 3 infections in the last 15 years. But there's nothing to boast about. This just you just keep your fingers crossed and follow the right sort of procedure what you're doing. There can be ligament injuries, as you were saying, that if one side is stiff and you're trying to balance it, you can overdo it, overcorrect it, and in that process you can cut the ligament. There's an iatrogenic injury. You can have knee dislocation. Our knee dislocation will happen if it's not well balanced. Aseptic loosening is the area which is long-term loosening. It wears out of life, and its main culprit is the polyethylene. And you can also have a periprosthetic fracture that following an accident after a knee replacement, you can break above or below the prosthesis. Now, I'll show you a few clinical slides. This is a disastrous complication from an infection. There's a rheumatoid patient that usually the blood supply and the skin is paper thin in rheumatoid. So when trying to do this, this is what it ended up with, and she had lots of plastic surgery input, flaps, and every cover. This is an infection as well, where you can see that it's like an abscess in front of the knee, and this is pus. Once you have a situation like this, that these knees are not, so you need to take the implants out, because with foreign bodies inside the joint, and what happens is that once you have done the knee replacement, gradually there is a slimy layer which forms around the component and the undersurface of the skin, which this biofilm and all the bacteria and everything go and reside in there. So even if you try to give them antibiotics, it's not going to work, and it keeps on coming back. So you need to go in the knee, you need to take all the components out, take all the bone cement out, wash it out thoroughly, and then to maintain the space, you keep a bit of bone cement in there inside the joint, just to maintain the space. You keep them on antibiotics, IV intravenous antibiotics, these patients, monitor them, see what their blood counts and things are showing, and over the next 4 to 6 weeks, you see what is happening. If you see that it's considerably gone down and the patient is improving, then you can go back and do another knee replacement on them. But you have to be careful, or else you need to fuse the knee at that stage, that both the femur and tibia, whatever is cut, that you fuse the knee. And with a fused knee, patients are able to walk, the leg is slightly short and it doesn't bend, but with a shoe raise, they can mobilize, they can maintain their, they obviously with difficulty, but they can perform some sort of function. So this is one area what we are all sort of very scared about, and we have to be extra careful in trying to prevent it. Ligament injury, you can see that in this case, this is the lateral side, this is the medial side, that there must have been some injury to the medial ligament. If you are doing in a rheumatoid knee, because in a rheumatoid arthritis patient, that the bones are soft, the knee is degenerate, and the ligaments and soft tissue are paper thin, are very sort of weak. So in those kind of situations, you will find that even though you have done a good job, that the post-op X-ray looks okay, with time that one of the ligaments may stretch out or tear, and then you can end up with a situation like this. If you have something like this, that the medial ligament either is very stretched out or it's torn. Now in this kind of situation, you need to, you cannot repair this ligament. You need to change this prosthesis into a more constrained one, like a hinge prosthesis, which will give stability to the knee. Otherwise, the patient is not going to walk on this type of knee. This is a dislocation that you see in this kind of scenario, that there must be extensive ligament injury all around the knee, and this happened, I think, following a fall. That the knee had dislocated. It's very difficult, because if you see this black shadow here, can you see this? This black shadow is the shadow from the plastic. This black shadow, we don't have that here. This is called the post. That this is built in posterior cruciate sacrificing ligaments designs, where you have this, which helps the tibia. This is not the right femur. That basically it's that prevents from the knee going forwards. Okay, this is called the cam and post mechanism, that it helps, it stops the femur from sliding anteriorly. But in this situation, you can see that it has crossed the cam and then coming forwards. Okay, so this is another kind of a situation where you would expect quite extensive ligament injury around the knee. So this prosthesis cannot be kept. So you need to take this off, you need to revise this knee and put a hinged prosthesis, which will give, the hinges will give it more stability to the joint. Now coming on to polyethylene wear, this is an extremely good, this is the paper which was published, that you can see that polyethylene wear is about 44%, and which is a main reason for revision of total knee replacement. Now there is loosening, instability, infection, and all the rest of it, but this has the highest sort of incidents, and because of this probably loosening is a sequel and thereby instability. So if you consider these three, you can see that this is a major concern for late loosening of the prosthesis. Now, why is it still a problem? What happens is these are all retrieval materials. You can see that it's worn out here, but with this centrally on both the medial and lateral side, it's quite worn out. You can see this side that almost this half is worn out. This is almost not that. Why does it wear? Now, there are three types of wear. One is an adhesive wear, which is directly related to the coefficient of friction because of this regular sort of movement and rubbing of the femoral component on the polyethylene, that you tend to develop this adhesive wear. You can also have an abrasive wear. Say suppose there is a scratch on this femur, that while inserting it, that it's not such a smooth polish, there is a scratch. So what will happen is that when with every kind of movement, that scratch area is moving there, and that is that this will be the abrasive wear. And thirdly, it's again an abrasive wear, but if you have a third body, a small particle of cement which stays there, or a loose piece of some worn out plastic which stays in between the bone and the tibia, and those will again give you scratching of the hard particles in the articulation, which is called the third body wear. And you have the fatigue wear. This is because of use over and over again. Now, what do we do? What are the solutions? To prevent your adhesive wear, the best way is to reduce the friction. So how do you reduce the friction? You need to reduce the friction. For abrasive, that if you are using a cobalt chrome component, then obviously it has to be smooth polished. There shouldn't be any scratches, and particularly you have to be very careful when putting it in, because they usually are polished. But when you try putting it in and then trying to put your femur or trying to use those levers on in and around the knee, you might scratch them, and that becomes a source of your wear. And you need to have a harder, less abrasive resistant counterface. And obviously it will depend on your implant design or the way you sterilize your poly and all these things. So this is what I wanted to mention, that this is Oxenium technology niche. This is a new one. This is not new, but the new design of this Oxenium is quite promising. What it is, a zirconium alloy. Now it is about 97.5% zirconium with about 0.25 or 2.5% of niobium, and it has been used in the nuclear industry for decades. It's a metallic element as the same family as titanium. It's highly biocompatible. There's no reaction in the body, and also has a very low modulus of elasticity, so it's stiff. Now, it is not a different sort of alloy. We have been used to zirconium because I don't know if you have heard about this ceramic implants. Now, for the hips, they have been quite successful. For the knees, it has not been as successful. Now, with it is more of an oxidation of the zirconium, which produces this Oxenium, and it's thermal oxidation. You just heat up this metal, and which turns into a surface transformation. There is a coating, and you get this Oxenium knee. So what are the properties? If you look at the coefficient of friction on polyethylene in a cobalt chrome, which is a standard design, that if you compare Oxenium, it's almost 50% less. If you look at the wettability, the lubrication, Oxenium and ceramic are similar, but they are much better than the cobalt chrome. So this is promising. This will reduce the adhesive wear in the polyethylene. If you look at their material properties, it has got increased surface hardness. So it is twice that of cobalt chromium. So if its surface is hard, that means there would be less of abrasion there. So this will supposed to last longer, and the oxygen enrichment aids in the ceramic adherence. So if you compare with cobalt chrome, it reduces the abrasive polyethylene again. So it's doing better, it's faring better against cobalt chrome. It is more abrasion resistant than cobalt chrome. So, and was one other important area is because cobalt chrome has nickel in it, and nickel is the only one which causes metal allergy. We do find patients occasionally who will complain of allergies to any kind of metal or in their body, and it's the nickel which is the culprit. So in those kind of situations, if you use oxenium, there is no reaction because there is no nickel. So this is another important role of oxenium femoral components, what we use in metal allergy patients. If you look at the knee simulator test that which measured in millions of cycles, if you compare the wear rate reduction, this green curve is for polyethylene, while the orange one is for oxenium. So you can see that the wear rate is a lot less compared to oxenium, compared to cobalt chrome, and if you it's about 85% less. And if you roughen the surface of polyethylene and then try it, still it's about 90% less. So oxenium is doing quite well compared to cobalt chrome. The only thing is that oxenium, we don't have long-term results yet. As I said, it's within sort of 15 years, 10 years results. We need to wait a bit longer to use it more freely. So where do we go in the future for knee replacement? Well, there have been areas of developments where people are still working on it. It's both clinical and engineering point of view. We used to do the knee replacements with a standard sort of midline incision in front of the knee, which was about 5 inches, and we expose the whole knee and then do the knee replacement. But now the downside of that procedure is it's an extensive wound, it's more painful, and it takes a slightly more longer time for patients to recover because of the pain and problems. But nowadays that the incision is getting smaller, you can do it with a smaller incision. You can cut the muscles in a different way so that you do less soft tissue damage, thereby less pain in the postoperative phase, early mobilization, and patients fare better. These are the two exposures which has come. One is the subvastus exposure. Our standard incision used to cut the quadriceps tendon and then go inside the joint and do it. But now they're lifting it up the quadriceps tendon. They don't need to cut it. So it's a smaller tissue damage even inside the knee joint. And also you can do a mini incision technique. There have been instruments and instruments which have been designed to do this mini incision technique. Computer navigated surgery is another area where what we do is that during the surgery or before the surgery, what you do is that there are trackers which you put in different areas of the bone on the patient on table, and then you register the patient, the areas of damage, and there are different points of registration what you take from around the knee joint. This is fed, these are the trackers. Now they are picked up by a camera on top and then are relayed onto the computer screen. The computer analyzes the degree of deformity, the computer analyzes the ligament balancing, how much it has to be there, and the computer will guide you on how much to cut or how to cut. And even if when you are cutting it, you are using the saw, the computer will give you the direction. So you would be very precise that if you if you think about doing the bone cuts, this is the margin, the yellow line what the computer is giving you. So if you put your saw, because that is got a tracker as well, that it has to be parallel to this line. It cannot be slightly tilted or inclined or anything like that. So once it's parallel, that means you are cutting it at 0 error. Similarly, on the femoral side, you do that. On the medial and lateral ligaments, where you are going to balance the knee, which will give you a success, they already calculate the degree of deformity or the strength of that on the either side. Okay, so the computer will show you till you are doing release of the ligaments. Computer shows you that when you have completed your release. So it's basically that you are going for zero error procedure. And if you have a zero error procedure, the usual sort of logic is that you will have better results, you would have better long-term results, and the knees won't fail from malalignment or malposition or not balancing it right kind of issues. However, computer navigated, there have been papers, there have been meta-analysis which has shown that you are, even if you are off by 3 degrees in placing your components or in balancing your ligaments or in performing a knee replacement, if you are either way 3 degrees or plus minus 3 millimeters, it doesn't have any effect on the long-term results. So computer navigation about 10 years back was in fashion, but slowly it's gone down a bit. But with mini incision technique coming in vogue, computer is again picking up, because with a smaller incision, you can balance your knees better with the aid of computer, because that gives you a guide. You can cut it better, you cut it more precisely, because the computer is helping you out a lot. Second, another development which has come in fashion over the last 5 years is patient-specific instrumentation. What happens is that we get a standard, when we are doing a knee replacement, we get a standard set of instruments and we get a standard set of implants to use. So when we start cutting it, we use those jigs and things which are standard. Now, not everybody's knees are the same. Some may be 2 millimeters bigger in anteroposterior diameter, some may be slightly flatter, some may be more rotated, some may be less. So what we do, what this procedure does is that we do an X-ray in the OPD of the patient, of the knee. We do a CT scan of the knees. Then it is sent it off to a lab where they process it in the computer, and then they make these molds for the cutting blocks specific for this person. Okay, then it's shipped here. Then you use this cutting blocks, as you can see that it's on the femur, that this block is designed, is molded, that this block is designed only for this person. So you will have a very precise sort of cut, that you can't falter on the cut or the size of the implant. And similarly on the tibial side, you get this cutting block. This is how it looks like, and with this slot you put in your saw and then cut the bone. The only criticism for this is that we don't have specific implants now, patient-specific implants yet, which will make it very expensive procedure to do. So that even if we are doing in a standard manner a knee replacement, if your femur, if somebody's femur is one size up or down, we do some adjustment that and use the standard, because you get this in specific 5 or 6 sizes, the tibias and the femurs. So you use it, you compromise a bit, but clinically you assess and see whichever is fits best, you use that. Now, if you spend a lot of money on the specific patient-specific jigs, but still you would come back and use the same implants. So it really doesn't make sense. If this comes with patient-specific implants, then it will make life a lot easier, but it will make the procedure very expensive. So I come to the end of my talk. Thank you very much. This is a first pictorial evidence of orthopedic surgery. This is in the 16th century, I think 15th century, somebody having his knee chopped. There's no anesthesia, there's 2 persons holding on to this chap, and there's, you can see the hacksaw. Much. Thank you.